Okay, so we are going to start. So, okay, well, so we are going to start. So, they're all good afternoon in Europe and good morning in America. I am Duan Cardona, Director of ICMA in Latin America. It's my great pleasure to preside over this conference on behalf of our research organization and of our organizing committee. First, I would like to thank the organizers, Alexandra Garcia Medina from Alliance Trained in Belgium, and to Edgardo Barraza Verde Soto from Minuto de Dios University in Colombia. They are a key team in our organization who assist us with their expertise in our scientific events and the research that we support in the area of data science, artificial intelligence, and machine learning. These are big ideas that shape our present and future. Mathematics is important here, helping us to understand complex information, predict things, and make smart choices. These ideas are not just about now. They are in the principal scenario of developments of our civilization. They will shake up industries, healthcare, and how we live. Welcome to this exciting journey of innovation and discovery. ICMA in Latin America is a research organization committed to promoting the visibility of mathematical research among our young generations in Latin America. Our team comprises approximately 50 mathematicians who are actively involved in organizing our congresses, satellite conference, and research activities. One fundamental aspect of our conference is that they were initially designed to engage the participation of Latin American countries. However, today, we welcome mathematicians from around 60 different countries. The ICMA and Satellite Conference in Data Science and Machine Learning 2023 is the last satellite conference that we organized this year. The first one, dedicated to algebra, combinatorics, and number theory, the past September, was a collaboratory effort between a young team of Colombian and Mexican mathematicians and saw the participation of 5,069 researchers. Our past conference in analysis and PDE has registered 585 participants, indicating that our activities are highly active and appealing to younger generations. Now it's my great pleasure to share with you that we have the participation of more than 300 researchers participants for this event. Summarizing, we have the participation of more than 1,400 participants in our related activities for 2023. This year, the 14th ISAAC Congress was held in Brazil at the University of Sao Paulo in Ribeirão Preto. This is the primary congress organized by the International Society for Analysis, its Applications and Computations. During this event, we were informed that ICMA in Latin America, in collaboration with Universidad del Valle and Universidad del Norte in Colombia, will be the organizers of the 17th ISAAC Congress in Barranquilla, Colombia, in 2029. This serves as a strong example of how our organization is diligently working to enhance the visibility of mathematicians in our region and is committed to advancing mathematical research in our areas. Subsequently, ISAAC began supporting the activities of ICMA in Latin America. Thank you, and may the Satellite Conference on Data Science, Artificial Intelligence, and Machine Learning 2023 serves as a source of inspiration, knowledge, and progress for our young Latin American researchers. Before finishing this speech, I invite all of you to visit our website and to register your participation to ICMA in Latin America 2024. We will have for this conference that will be held in October 2024 in virtual format also. And we are happy to confirm that, to announce that, among our plenaries, we will have the participation of Pierre-Louis Lyons from Collège de France, who award the Fields Medal in 1994, Peter Sarnak from Princeton University, who awarded the World Prize in 2014, Avi Vigderson from the Institute for Advanced Study in Princeton, who awarded the Nevalina Prize in 94, the Gödel Prize in 2009, the Nuke Prize in 2019, and finally the Abel Prize in 2021. Finally, we are happy to have also with us Efim Selmanov, who awarded the Fields Medal in 1994. So I really invite you to register your participation to have the opportunity to interact with these great mathematicians. Today, our first talk will be given by one of the giants in the fields of analysis and control theory. It's my pleasure to open this conference with the talk of Professor Dr. Enrique Suazua. We are going to start our program at 2 p.m. So see all of you at 2 p.m. when Alexandra Garcia is going to open the scientific program. So thank you to all the participants to be here. Thank you, really thank you for your participation. So we have with us our first speaker. Hello, Professor Suazua. In 3 minutes exactly, Alexandra will chair your session. Now, Professor Suazua, you have the permission to open microphone.
Ok, ahora sí, ¿no?
Ahora sí, profesor.
¿Me veis bien? Sí.
Sí, sí, profesor.
Voy a intentar conectar con el iPad, que es donde están las slides. A ver si... Perdonad, que es que aquí es muy temprano y estoy en el hotel y entonces tal vez la iluminación y el escenario no es el más adecuado.
Te vemos bien, te vemos bien. Si comenzaste a compartir pantalla, aún no.
Estoy intentándolo, pero dependo de la red local, si no tengo que poner el cable.
Muy
Estoy
bien,
verificando si va por internet y si no, igual los conecto por el cable. Sí, no me ha dejado.
muy
Al
bien.
estar en la red del hotel, debe ser una red un poco débil de invitados. Lo intento de nuevo ahora con el cable y si no, hago la presentación del ordenador. Ahora sí que lo veis, ¿no?
Sí, profesor.
Ok.
Faltan 5 minuticos para introducirlo, profesor, para que empiece a las exactamente a la hora.
Okay, Alexandra, go ahead.
Honor for me to introduce Professor Enrique Suazua. He is one of the great mathematicians in the world today. A brief overview of Professor Suazua's career will be the following. He is a professor at the Department of Data Science at the Friedrich Alexander Universität in Germany, where he holds a chair for dynamics, control, and numerics. He is also linked to the Autonomous University of Madrid, where he holds a strategic chair, and he is the director of CCM, Chair of Computational Mathematics at the Deusto Foundation at the University of Deusto in Bilbao. His field of expertise in the area of applied mathematics covers topics related to the partial differential equations, system control, numerical analysis, and machine learning. In 2006, he received the Euskadi Prize for Science and Technology. In 2007, he was awarded the Julio Rey Pastor National Prize for Mathematics, Information, and Communication Technology. In 2022, he received the CMWT and Idalia Red Prize for Fundamental Theoretical and Computational Contribution to the Control, Numerics, and Analysis of Nonlinear PDEs and Multiphysical Systems, among other awards. He is an honorary member of the Academia Europea and Jacques the Basque Academy of Science, Letters, and Humanities. Visiting professor of the laboratory Jacques-Louis Lyon of the Université Pierre et Marie Curie in Paris, and Sichuan University in Chengdu, China, and doctor honoris causa from the Université de Lorraine in France. Member and ambassador of the Friedrich Alexander University in Erlangen, Nuremberg, Germany. On this occasion, Professor Suazua will present his talk, Control and Machine Learning. Professor, you have 40 minutes for your presentation, later 10 minutes for questions. Now you can start.
Thank you, Alejandra. It's my great pleasure to be here. Again, congratulations for the work you are doing to put the Latin America community together and do it also open to the international community of mathematical sciences, and in this case, beyond, right? Because we are talking here about topics that are, beyond the borders of mathematics, getting into artificial intelligence and machine learning, that, as we know, is a very multidisciplinary field, right? So machine learning, artificial intelligence has grown from the input of different fields. Mathematics, mathematical foundations are very important, of course, but there was a great contribution done by computer scientists and definitely also from statistics, right? So actually, when you look how the master diplomas in artificial intelligence are configured nowadays, typically this is through this combination of mathematicians, mathematics, computer science, and statistics. And this is the way it has to be, right? Because the topic is very broad and the questions are very challenging, right? So nowadays, as we know well, and this is the reason why you are organizing also this workshop, one of these reasons certainly is that there is plenty of interest among mathematicians on these, novel topics of artificial intelligence and machine learning. And many of us are trying to, learn, understand, and maybe possibly trying to contribute. And I think, this is like when approaching a big forest you want to visit, it's impossible to, to have a complete view of the whole panorama. The landscape is wide and very rich and very beautiful as well. So, each of us has to enter this green forest of machine learning and artificial intelligence from a gate, right? And then, of course, it's always easier to choose the gate that is closest to you, the one that you see every morning when walking around. And this is what I did. Together with my team, I was very lucky to have, very brilliant collaborators that I will mention later. We decided early 2020, a bit earlier than COVID started, to explore this field. And then we did it from the topics we knew, right? Which is basically partial differential equations, numerical analysis of them, and also control theory. And then we discovered that actually control theory and machine learning are very closely connected. So here to the left, you see a video of a classical control theory simulation in which 4 dogs in blue, strategically are herding the flock of sheep, right? Of hundreds of sheep, that is, this red cloud. So on the left, you see a classical control theory application. There is no doubt, right? The 4 controls are the 4 dogs. Actually, in practice, the control is the shepherd that is giving very precise instructions to the dogs about how they should behave, right? And then the motion of these dogs is inducing indirectly the motion of the sheep, because the sheep are simply frightened by the dogs, right? So the sheep want to be away from the dogs, right? And then, trying to escape to each of these 4 dogs that through, by following the instructions of the shepherd, are building this kind of diagonal corridor, right? The sheep end up moving from the initial configuration towards the northeast to enter the gate. Of course, the sheep don't know they are going to enter a gate. They just walk according to their instinct, avoiding the presence or the proximity of the dogs. So this is a clear control problem. There is a state, the state is the position of these few hundreds of sheep, right, that we are interested on guiding to the gate. And there are controls, which are these actuators, the 4 dogs, that are being regulated, monitored by the shepherd that is on the background. Classical control problem in collective dynamics that you can easily extrapolate also to human behavior, to opinion formation in social networks, or if you want to, the irrigation systems or gas networks or electric networks, right? So the same ideas can be applied in a number of, say, applied fields of very different nature, neurosciences as well, right? And this belongs to the classical topic of control theory that was developed during the Industrial Revolution, right? Combining again the input from engineering, mathematics, and computer science that at the time was on its infancy. So now to the right, I can maybe show the videos again. To the right, you see another video in which 3 different populations of 3 different colors are evolving in different directions. So you see this, there is a crowd, very, mixed at the center, that eventually starts evolving, and then spontaneously this crowd, the different elements of this crowd identify each other. They realize, each of them, that they have a specific color in their t-shirt. So, and then the green cluster with the green, and then spontaneously, try to go into their own, say, table in the restaurant, right? So when you see this second video, you say, well, this is also kind of the same thing, right? Collective dynamics, except that now on the right-hand side video, we don't see the action of the controls, right? And the reason for this is that actually this second simulation belongs to the field of machine learning, and I am actually representing by this video the dynamic behavior of a deep neural network that is simply classifying data according to the labels. So this is, as you know, one of the classical applications in machine learning is, to classify data, like classifying in the hospital patients that are, healthy and those that are, under some risk, right? So we need to develop computer programs to do that automatically, because it will be simply too long to be done when you are dealing with hundreds of thousands of people or millions of people on a given, health system, to do that manually. The same when we are dealing with the, the qualifications of thousands of students at a given university, right? So we need machines helping us to do that, right? And this is what machine learning does for you. So on the right, the classical output of a deep neural network when solving this supervised learning problem, which is one of the simplest in the big field of machine learning and artificial intelligence. And then you say, well, on the right-hand side, this is not a control problem because there are no controls. On the left, there were controls, the dogs, the 4 dogs in blue. On the right, there are no controls. So this is not control theory. In fact, it is. Why? Because in order to build this neural network, this deep neural network, which is a time-discrete dynamical system that successfully is able to classify items according to their labels, their colors, you need to train, you need to find the correct parameters that are defining these neural networks. And these parameters are actually controls, right? Except that in the context of machine learning, where only few of the practitioners of machine learning know control theory, they will not call them controls. They will say, well, these are simply parameters that I have trained, using computer simulation, typically a kind of nonlinear, high-dimensional optimization problem that you solve using some kind of a stochastic gradient descent algorithm. But then these parameters are simply not drawn, right? Because what people are interested is not really on the values of the parameters of the neural network, but simply on the output and whether, the network was successfully able to classify items according to their labels. In this case, we got great success. Green are with green, yellow with yellow, and purple with purple, and there are no errors. We can say that we have achieved 100% classification rate. Of course, in practice, when you are dealing with realistic applications with huge ensemble of data, you are happy when you get it up to, some, percentage. But then people say, well, this is not control theory. But in fact, it's not true. It's the same as, in the context of the calculus of variation, we are interested on the minimizers or the critical points of a given functional. We know that in order to get these critical points, according to Lagrange, we need to pay attention also to the Lagrange multipliers. And then we say, okay, we accept, we go through the Lagrange multipliers, we compute the Lagrange multipliers to get the critical points. But once the critical points are achieved, we forget about the Lagrange multipliers. The same here. In machine learning, people know in order to build the correct neural network, they need to go through a very careful computation of the, the training of the relevant parameters. But once they are computed, they are ignored. And our point is that when you start paying attention to these parameters, you realize that, in fact, the two fields, merge, right? And the only difference between the video on the left and the video on the right is that in the video on the right, I didn't draw the evolution of the parameters in blue, because in particular, if I have drawn all the parameters in blue that are needed to build such a neural network, probably, our video will have become very, very messy, right? So this is the bridge between these two fields. And once you realize that this bridge exists, you're on the boat, because you can use all the know-how we have in control theory on the left, to be applied on the right. And you also, on the left, on control theory, you enjoy very much of all, the novel problems that emerge in the field of machine learning and that are feeding very interesting questions to the topic of control theory. So now, what is the model in which you can see more clearly this bridge? Well, so this is probably one of them. This is the so-called neural differential equation, which is just a differential equation, right? Which is determined by some coefficients, WT, AT, and BT, that are the parameters of the neural network to be trained, to be determined, so that the neural network, in this case, this continuous in time dynamical system, performs the requested task. The novelty in this differential equation with respect to other ones is that the nonlinearity is the so-called rectified linear unit, the ReLU. ReLU is simply the function that is 0 to the left and linear to the right. Very simple, globally Lipschitz function that makes the ODE to be well posed. Okay? And this is a nonlinearity, the ReLU, that typically you will not encounter in mechanics, where you will much more easily find, nonlinearities that are trigonometric or are polynomial, for instance. Okay? Now, this ODE is nothing but the continuous counterpart of the time discrete version, which is called the residual neural network. And you see it has the same structure, except that now is discrete on time, and therefore the parameters to be determined, WK, AK, and BK, are also discrete. These are the time discrete parameters determining the evolution of this deep neural network, which is simply a time discrete dynamical system. And this is just a time discrete development of, the classical static ansatz in the theory of, neural networks that, for instance, motivates the celebrated paper by Sibenko, when Sibenko says, listen, when you consider an ansatz like this, you are building a dense class of functions. So the same as you have polynomials and Stonne-Weierstrass, you have Fourier series, you have say infinity and compactly supported functions that typically are dense sets in LP, in Sobolev spaces. Well, here you have another one, right? And actually, it's not hard to understand why this ansatz leads to a class of dense functions, is because, in particular in 1D, when you draw how this function looks for sigma being the sigmoid, you see a piecewise linear and continuous function, right, that we know are dense, because this is, the foundational result for the theory of finite element methods, okay? So in the context of machine learning, density is named the theorem of universal approximation. Universal approximation means density, right? And then, of course, people were very happy when learning that such an object was dense, because once is dense, whenever someone asks you to, to build a function such that this and that, you can always say, well, listen, up to an epsilon error that you will never notice, right? I can build this function within this specific class. The only thing I need is to take k, the number of terms in this neural network, to be sufficiently high, right? And then determine or train the parameters wj, aj, and bj properly, so that your task is achieved. Now, in this passage from static to dynamic, the only thing we are doing, just to understand better, because we understand better nature as a space evolving in time, right? The only thing we do is that we deploy this sum, in which we are piling up all terms one after the other on a vertical column. We deploy it in horizontally along different steps of this, say, discrete or continuous dynamical system. So, this is the model which certainly bridges the two fields more clearly. And then when you observe what, normally machine learning practitioners do, what they will often do is for a given application based on the know-how they have, the experience they have on treating different problems in artificial intelligence and machine learning, choose a given architecture, the one they think is the more appropriate one for their purpose. And then, for every node in this, say, neural network, try to identify the parameters AT, WT, BT, or if you want in the discrete setting, AJ, WJ, BJ, right? Optimally, so to fit the data you are given, which something that is achieved by minimizing the empirical risk, and of course, adding some, mild Tikhonov regularization to guarantee the coercivity of the functional that is needed in order to assure that there is really an optimum or a minimizer. So now once you formulate the learning problem this way, you are led with a discrete optimization problem, typically in a high-dimensional space, right? In a high-dimensional space. Normally, this functional will not be convex simply because even though all this here looks like quadratic and linear, in fact, it is not, because there is the sigmoid, the ReLU nonlinearity embedded in the neural network makes that the dependence of the solutions X on the parameters is highly nonlinear. So this becomes a non-convex optimization problem in high dimension, for which, even though you can always guarantee that thanks to this, say, regularization term, a global minimum exists, it will be very hard to find methods that guarantee that you are really at this global minimum, sorry. So this is why you will deploy your know-how and stochastic descent algorithms to try to get at least to a local minimum, right? But, theory is hard to be developed in that setting. This is why, for a mathematician, there are many challenges in this context. And one of them is to, try to explain all this, right? So we have already given some, initial ideas of how a mathematician tackles this problem, but we would like to say more, right? So why machine learning, why artificial intelligence is being so efficient, despite of the fact that, the mathematical formulation of the problem becomes rather complex. And once we have understood why, explain the success of the present method, of course, our goal will be to develop, say, novel family of, say, methods that could be more efficient, computationally less expensive, more robust, and so on, right? Of course, the task is huge, right? Because, this is just a collection of the kind of architectures that computer scientists used in this field of machine learning and artificial intelligence. And you see that there are a few architectures that have been developed for different purposes. So, of course, from an analysis perspective, each of these architectures requires an ad hoc analysis, and therefore, the number of challenges and the beauty of the questions you can encounter is really fantastic. Okay, so this is a topic we started working 3.5 years ago or so. As I said, there is a short ICMAM News article published 1 year ago where we say summarize our perspective to this topic, is somehow the synthesis of this talk. And there are some other papers published with Borjan Geskowski, who is now a postdoc in MIT in Acta Numerica, with Dominic Ruiz-Vallet, who is now postdoc in Imperial College London, a couple of articles in Science Review and in the journal de Mathématiques Pure et Appliquée. Okay, so now to better understand what we did, it's good to have a quick look to what control theory is. So Norbert Wiener, back in 1948, so almost 65 years ago, right? Or 75 years ago, he defined cybernetics, control theory, as the science of control and communication in animals and machines. And then when you think of this definition, science of control and communication in animals and machines, you wonder, well, but maybe this could also be the definition of what machine learning should do, right? Actually, one of the seminal results in control theory back in 1958, 10 years after, formulated properly in this way by Rudolf Kalman, said, so here should be a D, sorry, is the following. He said, okay, let's consider a model, right, just to make things properly formulated in mathematical terms. Let's formulate this model in which you have a linear dynamical system. So you have a state. The state is X, is a d-dimensional state. It can be one of these shapes evolving in the three-dimensional space or on the plane, or it could be maybe the state of mind of d individuals in a social network, in which case the dimension could be millions, right, of them, or could be, the different cities, how well they are served by gas or electricity or water on a country, again, thousands of towns, right, in a different country. So it can be a vector of low dimension or high dimension, depending on the application you have in mind. You assume that the dynamics, the free dynamics, is driven by the matrix A. Of course, you can move into, say, PD operators as well, time-dependent or nonlinear, but just to make things more clear here, I assume that all the dynamics is driven by a D by D matrix. And then you have some controls, exterior forces, right? Like, for instance, the heating, system, or air conditioning, the cooling system, so to regulate the temperature in a huge building, right? That could be the case. And then, the heaters are modeled, the actuators are modeled by B. So the actuators are, described by B, and you are simply, the controls you can implement, the actions you can implement on it. So in particular, in practical applications, we are interested in cases where D is huge, like a social network, and M, the number of influencers, is very low, right? So in this case, for instance, you see in ICMAM, there is a small group of people that is influencing a broad community of mathematicians that, guarantee that the success of events, so that, dozens of people can meet today morning, right, to listen and deliver this talk. So this is a typical case of a large network that is regulated just by a few controllers. So, and then Kalman said, can it be that I am able to control a large dimensional system by just using a few controls? And then, you can prove an if and only if condition. And the if and only if condition is that the rank of the matrix B up to A D minus 1, here it should be a D B, is equal to D, right? So if this rank condition is fulfilled, indeed, you can control this huge dimensional system by just a few controls. In case, you are not lucky and you have chosen a control operator B, the location of your actuators in the building are not sufficient, and then you have, for instance, here D minus 1, I'm sorry, one of the rooms will not be heated, right? That's the conclusion. Now, this is an if and only if condition, so mathematicians are happy. In practical applications, of course, that's not that easy, right? If I give you big matrices A and B, and I ask you, can you please check that the rank of this super matrix is equal to B, you will say, well, Enrique, this is not fun. And in fact, one of the greatest, developments in the interface between machine learning, artificial intelligence, and mathematics last year was, the DeepMind new algorithms in order to fasten the process of multiplying huge matrices, right? So you see that somehow, we are in a loop, right? We want to use control theory in order to better understand the challenges in machine learning. But then when we go back to the most classical results in control theory, we realize that some of them already, just to check whether this rank is full or not, will require of developing very high dimensional computations, for which you really need the help of computers and artificial intelligence again, okay? So, but, more classically, this is how things are, right? So the classical applications, as I have said, of control theory are in the Industrial Revolution, for instance, optimally parking a car, and then, this is how you do, right? If someone tells you, do you know how to park a car? Then you will say, yes, I know control theory, so I develop all the modeling, and I do, the Pontryagin maximum principle, and I compute the optimal solution. And once you have the optimal solution, you implement it, and this is how nicely you are able to park the car. As you know, in practice, it's not that easy, right? And it's not that easy because humans, we struggle to implement, to figure out what the optimal strategy is and to implement it. So much before this application to automotion, there was the first paper in control theory. The first, more scientific paper in control theory was written by Lord Maxwell, the same as in electromagnetism, that was analyzing the stability of the ball regulator engine for governors, the key, tool in the Industrial Revolution. And this is how, as I have shown you before, you can also deal with other high-dimensional applications like collective dynamics, and, for instance, develop the simulations I have shown you before of how 4 dogs can herd a flock of sheep. Okay, very good. Now, this was classical control theory. What about machine learning? Well, in machine learning, as I said, we want to build machines. So for building a machine, you need to build an algorithm. So we need to build an algorithm that is able, for instance, to classify trash. We are very much in the spirit of Wiener, right? We want to build a machine that will automatically do something that we can do, definitely, right? But we don't like doing. So if you ask me, can you classify trash? I tell you yes. So plastic goes to yellow, glass goes to green, paper goes to blue, and organic goes to gray. And, to a large extent, I can really identify, split, separate different objects, and I can classify trash. But I don't want to do it. I prefer that a robot, a truck, does it for me automatically. So how do I build this robot? I need to build a function. I need to build a function from RD into RM. So what is RD? Well, it's the space in which all these objects are living. You tell me, well, these objects, they don't live in a Euclidean space. Well, they actually do. You take photos, each photo of an object is just a number of pixels. I don't know, 250 times 250. So maybe you are in dimension 60,000. Okay, but every item is a point in an Euclidean space of dimension d, which is of the order of, say, thousands. So very high dimensional Euclidean spaces. So you can put every item in this space. And then what you have to do is to guarantee that you have a function so that whenever, the item is made of plastic, it goes to a label that could be, for instance, one of the 4, say, points in the, on the Euclidean plane. So you can take, for instance, m equal 2, right? And then simply take the North Pole, the South Pole, the East, and the West as the 4 destinations for the 4 different colors. Can you build such a function? Well, what you do is you train this function. What does it mean, you train? Well, you guarantee that at least in these 32 examples that you are given here, right, on which you can learn, you do it carefully so that, the function f takes every plastic object and bring it to the North Pole. And then it takes carefully every glass, item and brings it to the South Pole, and so on. And once this function is built, you are somehow interpolating all this discrete data you are given. Then you hope that this function will be able to generalize well. This is the objective, right? So the objective is not to classify these 32 objects. This is something everyone can do, but is to build a machine, to build a function so that whenever you bring a new object, this function will spontaneously, bring this object to the corresponding basket according, to its nature. So that whenever, someone comes, with a new bottle of mineral, water, the machine will check, oh, is this plastic or is this glass? And according to it, it will go either to yellow or to green. Okay, that's supervised learning. And supervised learning works. These are the videos that Borjan Geskowski has developed. We have done this applying our know-how in control theory by exploring and understanding the nature of this neural differential equation that, as I have shown you, is the most natural model to be employed when you are a dynamical system person, right? And it works, it's able to classify items according to their labels. In this case, in this video, there are only 3 colors, 3 different types of materials, say plastic, glass, and organic. Okay, and then the fact that this can be done is formulated in this paper that I mentioned before, published in Science Review earlier this year with Dominic Ruiz-Vallet, in which, you don't need to read this statement. It says, yes, we can, in the sense that regardless what the dimension of the Euclidean space is, you need dimension greater than 2, because otherwise, of course, in 1D, the different items will collide. Regardless what the dimension D is, regardless how many items, capital N, you have, and how many classes M, different labels you have, you can always build a dynamical system of this type of neural differential equation that will bring every item to the corresponding destination. So what we show here is a huge, say, ensemble or simultaneous controllability property of this neural differential equation. And when I say ensemble or simultaneously, what I mean is that the same dynamical system with the same controls and parameters is able to drive each item to the destination, right, simultaneously, right? How do we do that? So why this works? Why this huge ensemble controllability property is fulfilled for this system? Well, it's because of the very nature of this sigma, of this ReLU. Why ReLU is so important? You recall, ReLU was this very naive function, 0 to the left and linear to the right. Why this naive function is so relevant? Well, because it allows you to split the space in which data are evolving, the items are evolving in 2 halves. Recall, X of t is what? X of t is this bottle of, say, glass that is living in this high-dimensional Euclidean space, and that is moving, like in the Disney movies, right? Is moving from the initial location to get to the corresponding, reservoir of glass items, the green basket, right? So take any of these items you are dealing with, right? The same application, of course, works. This is what, your computer does when you open the folder of photos in your computer and you say, oh, there are 10,000 of them. And you say, well, I want to put order. So, then you open a folder for every, of your colleagues, friends, and family members. And then you try to do one by one. You open, this photo and you say, oh, this is my mother. So it goes to the folder mom. You open another folder and you say, oh, this is my brother. Then it goes to the folder brother, and so on. But after 100, at most, you will be bored. You will abandon. And this is when you say to the computer, please do it yourself. Of course, the computer will tell you, before you ask me to do it, you have to give me the name of each of the persons in your folder at least once, right? But then when you choose, the photo of your brother and you put its name on it, like, Peter, right? Then the computer will immediately generate a folder with Peter and will put there all the photos of your brother. Then you have to supervise. You have to check whether the folder has, the automatic process has done it successfully. And you see what you discover sometimes is that, well, it's very well done. It's not perfect, though, because you open the folder of your brother, Peter, and you see that one of your photos is there. But the reason for that is that indeed there are similarities between your brother and you, and this is what makes, of course, the computer to get confused. But it's certainly much faster and better than how any human could develop this simple but boring task because of its size. Okay? So then why this neural ODE is able to do that so efficiently for us? The reason is the following. You see, keep in mind that sigma is like this, right? 0 to the left and then linear to the right. Okay? So sigma is a scalar, x is a vector in RD, AT is a vector, this dot means a scalar product, B is just, a scalar number, it's just a real, and then WT is again a column vector, right, of dimension D. So you have here D parameters, and one parameter, 2D plus 1. What are you doing? So actually in here, you see this is a hyperplane. A dot x plus b equals 0 in the Euclidean space is just a hyperplane perpendicular to A, and B is just a translation of this hyperplane. And what happens then? Well, sigma will be 0 on one side of this hyperplane and then linear on the other side. What are we then doing? Well, what we are doing is we are choosing W, is the direction of the wind. So what we are therefore doing, basically at every time instant, we are dividing the Euclidean space into two halves, determining which half is active, which one is frozen, and in the active hyperplane, we are just choosing the proper direction of the wind. And our claim is, in that theorem, that if you do that properly, in a finite number of consecutive steps, your ODE will classify all the items. Basically, we are doing the same as when solving the Rubik cube. By the way, when you watch the video of the DeepMind company, how they develop these new algorithms to multiply matrices, they also tell you about the Rubik cube, right? You see that they did it, indeed inspired on how we organize the task for solving a Rubik cube. And somehow we are doing the same, right? Because when you start with a Rubik cube, which is disordered, you have micro phases totally disordered, right? And then solving the Rubik cube means bringing each micro phase to a big phase coherent according to the label. So, and what we do for solving this problem, we know that the Rubik cube is solved in a finite number of iterations, and in each iteration, half of the cube is kept frozen with one hat, while the other one is rotating in a strategic direction. And in this way, inductively, the same way you can solve the Rubik cube, you can solve our simultaneous control problem. Let me just give you an example, how you just classify one item. Because once you learn how to classify one item, then you can do one after each other. You can classify as many as you need, okay? So in this example, you see we have 9 items. Out of them, 8 are well classified, but there is one that is misplaced. So the blue item is in the green basket. So the goal has to be bring this blue item to the blue basket. But of course, while doing that, you need to preserve the fact that the other 8 are well located in the corresponding baskets. How do we do that? Well, I claim that we can do it just combining 4 different constant arcs on this neural differential equation. In the video, I show you how 4 motions suffice. In each motion, you will see that the screen is split into 2 halves. The dark one is the one corresponding to the frozen, right, half space, while the color one is the one that is moving. And in this particular application, just to make it more simple, in this particular construction, I'm just using hyperplanes that are horizontal or vertical, right? Although I could use oblique hyperplanes and oblique, wind direction, so to maybe be able to solve the task, not in 4 iterations, but in 2. But in here, we are not trying to be the world champions on the Rubik cube. We just want to solve it, okay, in a decent manner. And this is how it goes. Left frozen, right goes up. Down frozen, up goes left. Up frozen, down goes left. And then left frozen, right goes up. And the blue gets to the blue area while the others remain in the corresponding baskets, okay? So once more, left frozen, right goes up. Down frozen, up goes left. Up frozen, down goes left. Left frozen, right goes up. Okay, good. This is the proof. Now, normally you will find that neural networks are not written in an incremental manner, but often these are the so-called recurrent non-residual neural networks. You apply sigma again and again, one after another. And this is, in this case, then the nonlinear dynamical system is harder to be understood. This has been done by our PhD student Martin Hernandez from Chile that is working in our group in Erlangen, right? This is a bit harder to understand. But again, this can be done. So mathematically, you see that we need a width, again, of 2 dimensions. So you can take items in a very high dimensional space, project them into, low dimensional ones, like, in the classical theorems of Johnson and Lindenstrauss and so on, right? But here you do it really practically. You go from very high dimension to 2D. And once you are in 2D, you try to reshuffle, reposition the items according to this, say, nonlinear activation, exercises, until, you get all items classified according to their labels. So in this case, the sigma is a vector valued function that is simply taking each of the coordinates of the vector and applying sigma independently to each of the coordinates. So now sigma is a vectorial function that is simply mimicking the action of the ReLU, but in each of the components. And now there is no W here, you see. You have just the A's and the B's. You have to understand how to determine the A's and the B's to succeed. And the claim in our paper with Martin is that with width 2, so just taking D equal to, just a neural network of 2 components, is able to do that in 2n plus 4m minus 1 steps, n being the number of items to be classified, and m being the number of classes, number of baskets, okay? So how do you do that? Well, it's more or less the same geometry as before, with just one further observation. So when we have just a neural network and only, one sigmoid ReLU, only one, we are splitting space into 2 halves. We have said that. One of them is frozen, the other one is active. But when we have 2 of them in a vector manner, we are dividing, right, the space, the plane, into 2 different, with 2 different equators, right? So therefore, you are generating 4 different regions. In this region here, both of the sigmas vanish, and therefore all points in this, sector will go to 0, 0. While when you are in any of these 2 sectors, one of the sigmas is frozen, but the other one is active. And this is why these points will move. And they will move to points either in the vertical axis or in the horizontal one. And it's only the points that are, in this 4th sector, in which both of them are active, that really move in a 2-dimensional manner to occupy any of the points in this quadrant, right? That's the idea. So now the question is, depending on how you choose the parameters A and B, of course, you are collocating these hyperplanes differently, and therefore you are making different choices of how the different sectors should be moving. The claim is, if you do that in a smart manner, in a finite number of, iterations, you will succeed, right? And this is what the video shows, right? Okay, so first you go into 1D, and then
Sorry, Professor.
Yeah?
How much time are you planning to talk?
I finish in 5 minutes, right? This is what you told me.
Okay, perfect. Yeah. because yes, continue. Thank you.
Okay, so you see how things succeed. Well, because we are getting short of time, I would like now to try to conclude, right, with a number of comments on what are the perspectives, right? So what has been the context of our lecture? So first, we have said there is a clear bridge between control and machine learning. Actually, one could even claim that machine learning is a descendant of control theory, right? We have seen how the success of machine learning, in particular in the problems of supervised learning, for two very different architectures, the residual neural networks and the recurrent nonlinear neural networks, can be understood once you bring, your know-how of control theory into play, right? So we were able to contribute to the mathematical explanation of the success of machine learning. I have also mentioned there are many, many different topics you could consider. In particular, you could address the different architectures of the neural networks and then try to understand the maths of them, right? And then you will in particular say, well, this one is better than the other because, for instance, the complexity of the number of iterations needed, the number of parameters that are needed to solve them, is lower in one case or the other, right? But in fact, when you think more broadly, you see that we have also established links with other fields, right? So in particular, we have established a clear bridge with the theory of optimal transport, right? So why? Well, because solutions of ordinary differential equations are nothing but the characteristics of a transport equation. And what we have shown is that we can build these differential equations in a way that every item is transported to the corresponding destination. So in some sense, what we have done here has been very close to optimal transport, except that in our case, we didn't guarantee that the transportation cost was optimal. What we did rather, because we were somehow motivated by neural networks, what we did was to guarantee that the vector field had a neural right shape. So what we did was to develop a variant of the optimal transport to say, well, maybe our transport maps are not optimal, but they are neural, right? And of course, this is also related to the problem of normalizing flows when we are not only aiming to control simultaneously a finite number of items, but through this process, we want to develop neural networks that are generative, that are can generate new scenarios like it happens in this web page. This person does not exist, that every time you click interpolates among millions of pictures and generates the new image of a person, a new photo of a person that doesn't really exist. So this bring us naturally into the field of generative machine learning. So this is the end of my talk. I thank you again for your kind invitation and for being so successful on putting our community of Latin America mathematicians together and together with all the other colleagues. And I invite you to somehow to join the community of mathematicians working in this area. There is really so much to do, in particular, as I said, to better understand, how machine learning works. And once this has been done, to develop new methodologies that probably will be, more robust, cheaper, and more efficient. Thank you for your attention.
Thank you, Professor Enrique. Now, are there any questions for Professor Suazua? participant. You can write the question if you want in the chat too.
Question. Professor Suazua,
Sí.
of all of the challenge that mathematicians have when working in machine learning, which would be, in your opinion, the more remarkable ones, especially for people working in partial differential equations?
I mean, this is a very good question, right? So I think there are at least two different avenues to tackle this question. So one of them will be use machine learning for PDs. That's one possibility. So in particular, can you use machine learning to better solve, for instance, inverse problems for partial differential equations, right? That will be one possibility. Use machine learning to solve better PD problems. So use machine learning as a complement to the existing numerical analysis tools, right? This certainly can be done, but very often without guarantees. Why? Because I have explained before, normally machine learning goes through a huge non-convex optimization problem, and then you apply stochastic gradient descent, you will get great simulations, right? But probably without convergence guarantees. And then the question comes back to you. It's like a boomerang, right? You use machine learning to solve PD problems numerically. You will show to your colleagues, you see how great it is. It goes very fast. I get fantastic simulations that, before, I was taking longer to achieve. And then people will ask you, can you guarantee convergence? And then you will encounter new mathematical problems that are related to the mathematical foundations of machine learning again, right? And now, maybe just to refer to, the last slide I was showing, this is a remarkable example where you see, the emergence of PDEs again, right? So we're thinking on discrete data. As soon as you think on density functions, you are in the context of, say, transport PDEs. And then, you being maybe an expert in fluid mechanics, you will have plenty of ideas of how to contribute to this area, right? So this is a third, maybe, possibility, just to say, okay, I choose one of these interface topics like neural transport and try to bring my know-how of hyperbolic equations and fluid mechanics into this field.
Thank you, Professor. Carpe Diem wants to do a question. Carpe Diem, please.
The chat, someone write one question, the Dr. Viswarajan Senasapi. He said, any thought of machine learning models in quantum computing applications?
Yes, so what is the question? Sorry.
Any thought on machine learning models in quantum computing applications? In the chat, is there the
I see. So this is certainly a very good question. So quantum computing is in itself a great challenge for mathematics, right? And therefore, yeah, certainly, again, you can use machine learning on it, right? So that's certainly one of the possibilities. I have shown you actually how you can use machine learning for linear algebra, right? Because, and of course, if machine learning is used in linear algebra, right? So it can also be used in the new algebra you have to develop for quantum computing, right? In particular, as soon as you get into high-dimensional problems, right, you will need to be assisted by machine learning tools to be able to run these computations efficiently and fast.
Sorry for everyone. Maybe the question, you can send this question or email, because we have other presentation in 5 minutes. for the Profesora Camelia Goga. For that, now, Edgardo, you can continue with the professor.
Thank you.
Camelia, and thank you so much for your talk, Professor Enrique.
Thank you, Alexandra. It was my great pleasure. See you later. Thank you again. Bravo.
Thank you, Professor.
Gracias.
Sorry for the other participants because the next lecturer is ready. Professor Camelia, are you here? Are you there? Professor Camelia?
Okay.
The professor is
Now Professor Camelia has the permission to open your
Yes.
microphone.
Yes,
Okay,
now I have the
okay,
permission to
okay,
put my mic.
okay, no problem.
Yes, hi
Okay.
everyone. So I can so just tell me how should I proceed?
Okay, Professor. Could you share your screen, please, with your presentation?
Yes, just a moment.
Okay. First, I should present to you.
Is it? Can you see my presentation?
Yes, yes, very good. Okay. Good morning and afternoon for everybody. Today we have the privilege of being in the presence of a great researcher and leader in the field of machine learning. Our guest speaker has dedicated her career to finding innovative solutions in this field. Professor Camelia Goga has doctorate studies in mathematics and statistics from University Rennes. She serves as a statistics professor at the University of Bourgogne-Franche-Comté and is a member of the Probability and Statistics Group at the Besançon Mathematics Laboratory. Additionally, she has been the head of the master's degree program in statistics modeling in Besançon since 2018. From 2015 to 2017, Professor Camelia served as the director of IREM Dijon. Since 2019, she has been an associate editor of the Journal of Non-Parametric Statistics. Her areas of expertise encompass survey theory, non-parametric statistics, statistical learning, and accident forecasting. Today, Professor Camelia will be sharing her talk titled Model Assisted and Calibration Estimation in a High Dimension Settings for Survey Data. Professor, you have 40 minutes for your presentation. Later, 10 minutes for questions. Now you can start.
Thank you very much for this very nice presentation. Thank you also for inviting me to give this talk today. I thank especially Andrea. I hope she's doing well in her PhD study. So my main, as you said, my main research is in survey sampling, and for the last year I'm interested in studying how machine learning methods can be used in this framework. But today I will speak about something a little bit different, how dimension setting, how they will influence the traditional methods that have been used for the last 30 or 40 years. So I will speak I'll speak with giving you a very short motivation of results presented today. It is about the estimation of finite population totals. We are usually interested in a survey sampling framework with this very sample parameter. But when we have a very large number of cover rates or auxiliary information data set, as we usually call it, I will show you that in this situation, the traditional model-assisted estimator or the calibration estimators will have some problems, and I will show you how to improve the traditional estimators by considering methods borrowed from the statistical linear modeling regression, such as the penalization or the dimension reduction methods. I will finish, I hope I will have the time to show you a short simulation study on real Irish electricity consumption data. So my presentation from today is meant to give you a review of several results that I have done in collaboration with several researchers and with our PhD students. First of all, with David Aziza from the University of Ottawa, and our PhD student Mehdi Dagdouk from the master degree from Besançon, then Guillaume Chauvet from NSAI in France, and Hervé Cardo from the University of Burgundy, and Mohamed Shehzad, who is now in Pakistan as an assistant professor. Also, Mehdi Dagdoun is at McGill University as an assistant professor too. So today, as everyone knows, we have very much digital devices such as smartphone or smart meters, which are capable to record and also to send the information at a very fine scale. For example, every minute or even every second. So in this situation, even the surveys conducted by national statistical offices are not exception of these rules, and they have now access to a very large data set which are recorded for a large number of individuals, and especially for a large number of variables. So in this new high-dimensional setting, as you know, new challenges appear, and we will see that the traditional, we have seen in a statistical traditional framework, but also in a survey sampling framework, that the traditional parametric or non-parametric estimation may prove inefficient. So just take a little example. You may maybe know how a smart meter works, but just this same simple picture. You have your smart meter that may be installed in your home in order, for example, to record the electricity consumption and to send it, for example, every 30 minutes or every 10 minutes or even more every minute to a utility office by means of some communication device. So these kind of smart meters are usually used by many countries, and France is one of them. More exactly, for the last 10 years, the French electricity company have installed more than 30 million smart meters in almost every house and every company. How looks like the information that we collect with such smart meters? For example, if we take a population of more than 18,000 companies, and we record the electricity consumption every 30 minutes, we will obtain something like that for 1 week. I have considered here only a period of only 1 week. And for more visibility, I have plotted only 5 electricity consumption curves. I have used different colors. So we have now, for 1 week, we have 336 measured instants. So we can see that the instant measures are so close, so many, that the observation is now considered more like a function than as a multivariate vector. So we can remark something that it is some kind of a periodicity over the week. We have high consumption during in the middle of the day and low consumption during the night. We can remark this better if we plot the mean curve here in red. So we can remark the 5 peaks of consumption during the week and low consumption during the weekend. We can plot also some more robust indicators, such as the median curve, which is here plotted in black. We remark the same periodicity, but with lower, as expected, with lower values. So I know very well this kind of data because for 10 years we have, with my colleagues, we have worked with the French electricity consumption, who was interested at that time when they started to install these smart meters. In fact, it was too costly and the information was too large to keep it all. So their goal was to estimate the whole the total electricity consumption by means of a sample of individuals selected randomly from the whole population of companies and households. And the goal was to find the best strategy, namely how to select individuals, but also how to estimate this interest parameter in order to have the lowest variance of the used estimator, because the final goal was in fact to build some confidence bands of our mean total curve plotted here. So, we had a lot of work done on this subject, and at this time, the electricity consumption is using a survey sampling design in order to select companies and households, and not to keep all the information. A second example is again the curves, but the audience curves recorded by Mediametry, which is a company, the private company with recording any kind of audience in France. And they have the same smart meters to record the TV audience, for example. But here the information is even richer, because the audience is recorded every minute. So we have only 5 curves here for a period of 1 day. So you can see that again the information is even richer, because we have more than 1,400 instant of measure. And again, we have more like a curve, which is less smooth than the first electricity curve, but we have a function and instead of a multivariate vector. So these are 2 examples that I know very well, because I have worked with these 2 companies, but today we have many examples. And in this high dimensional data set, and in fact, there are many new challenges. First of all, we may ask what we are estimating now. And then, especially in a survey sampling framework, how we will estimate what you want to estimate. And for example, if we want to use a simple linear model, which are our covariate, and how can we use to improve our estimator, knowing that we have a large number of covariates. So I will address in my talk the second part. So the idea is to use all these high-dimensional covariates in order to improve the estimator that there were existing already. I will start by giving you briefly some notation and some specificity of survey sampling framework. You may not know this part of statistics, which is a little bit different, because in general we do not suppose that our individuals are selected independently from the population, from an infinite universe, but they are selected according to a probability sampling design, namely a function P, which will give some known probability to each sample from our population. Once that we decide that the sampling design, we can compute the first order inclusion probability denoted by pi k and second order inclusion probabilities, pi kl, which are in fact the probability that an individual is selected in a sample, and the second one is the probability that a couple is selected in a sample. In fact, these two quantities are very important. The first one for building the estimator, and the second one for estimating the variance. So as I said, we want to estimate a total. That is nothing simpler than a total. And the estimator that is used, the basic estimator used in this context is what he called the Orvis-Thompson estimator, which means if everyone from the sample is responding, we have yk, the yk value, and we weight by the inverse of the inclusion probability. So we dilate the value of the sample individual by this sampling weight, 1 over pi k, and this way the sample individuals, they account for the non-sample individuals. In this expression, something that is different from the statistics, the classical statistic, yk is not random, but the selection and not selection in the sample is the random variable. With under the sampling designs, the expectation of this indicator is pi k, and so we'll obtain, in fact, an unbiased estimator for the unknown total. We can compute the variance, which we can see here. The non-independence of individual selection of individual implies that we have here pi kl, and if all the couple have a non-zero probability of being selected, then we can estimate unbiasedly this variance, which is unknown, because we can see here that we have double sum over the whole population, which we do not have. So just take a little example. We will have the simple random sampling without replacement of size small n. So this means we take an individual from the population, just we put away from the list. We take another, randomly another second individual from the list, and we put away. And so we repeat n times. This is the simplest, one of the simplest random sampling. In this situation, the estimator is very simple. All individuals have the same probability of being selected, n divided by capital N, and the variance will be here. Given here, we have a constant. This f is the sampling, small n divided by capital N, and here this is important. It is the variance of y over the whole population. So if we have very variable variables, just like the wage, for example, this variance will be huge, very large. And we can do nothing about it. At least everyone will earn the same thing, or very similar. So this means that the strategy with Orvis-Thompson and the simple random sampling without the replacement will be a better strategy if we want to estimate the total of variables that are with very high variability. And the idea is how to improve this strategy. And in order to improve, as everyone knows, we can consider extra information, which as usually is given by some auxiliary variables or covariates, if we use the name given in a case of a model, and denoted as usual by x1, xp. So we have the data matrix, which in case of a survey is not known for all, may not be known for all the individuals. Because, as I said before, we don't have access to all the information by reason of confidentiality, for example, but we can know for some X, we can know their total. We can know how many women are in the whole population, or the proportion. We can know what is the proportion of young people or the older people, but without knowing for each individual exactly his age, for example, or his sex. So we can use this information to build a better estimator than the Orvis-Thompson estimator that I have presented before. This information, the information, auxiliary information, may be used to build a better sampling design than the simple random sampling presented before. But in this case, we need to know X, okay, for everyone in the population. So now, how can we build a better estimator? There are several approaches. I will present you two approaches that I am concerned in my research. The first one is based on a model, on a superpopulation model. So we suppose now that YK is a realization of some variable, a random variable, and the relationship between Y and X is given by a model, just everyone knows, where the regression function M here, we can suppose that it is unknown, for example, but smooth function, and the residual are independent of and of zero mean. This is the least requirement that we can do about this model. And then how can we estimate T or Y, the total of Y? In fact, we will consider the population total of the estimated estimation of M, but we will add some correction term instead in the case where the model is misspecified. In fact, we have something that it is assisted by the model and not based by the on the model. If the model is not good, this estimator will still be consistent for our total. So how can which model can we have here? So I will consider the simplest situation of a linear model, as everybody knows, with unknown beta coefficient given here, that will estimate now is a survey sampling techniques in two steps. We consider at the beginning on the population level by ordinary least square. We have the well-known optimization problem, which gives us the expression of beta OLS, and we can see on this expression that these quantities may not be known, and this one is surely not known because Y is known only for the sampled individual. So we'll estimate the coefficient of regression at the sample level by considering Orvis-Thompson estimator for each unknown total. So we'll obtain some expression that is similar to the one that everyone knows, but now we have weights, the sampling weights in both terms from here. So we can see that this is a nonlinear function of totals, which will complicate the derivation of the bias and of the variance of the estimator, what is called the model assisted or Greg estimator of the total, which is obtained by plugging in the unknown beta by hat beta pi. We'll obtain this new estimator, which is in fact the Orvis-Thompson estimator presented at the beginning of my presentation of Y minus this vectorial product. We have here the Orvis-Thompson estimator of total of X and the estimator of beta. So remember that for X, I said that we need only to know its total over the population. So we can see here we need this quantity. And on the sample, we need to measure X only for the sampled individuals. The result is that we can write this new estimator as a weighted sum of the Y values, where Y is the value of the variable for the sampled individuals, with weights. The weights, in fact, are very important in survey sampling theory. And here the weights are a little bit complicated, but what is important is that are independent of Y. So we can apply to some other, for estimating some other totals. Now we have this new estimator, but remember that we want to improve the strategy that we have at the beginning based on the Orvis-Thompson estimator. Improving means better variance, better smaller variance. And the little bit problem that we had here is that this estimator is a little bit complicated, then it's not linear in quantities for which we can derive easily the variance. We must use some approximation formula. Donc the one that it is very quick is to write the sampling error. There's a difference of two terms. The first one is very similar to the estimator that I have presented to you. And the difference that here we have the estimator of the coefficient of regression, but computed at the population level. So this quantity is not random with respect to the sampling design. We can write this estimator as this sum. The first term is not random, and the second one is a Orvis-Thompson estimator for the residual of y computed at the population level. So we compute very easily its variance, its bias, and its variance. So this one, the first term, is it can be handled very easily. And the second one is kind of a reminder term, and this term it will be very small, then we can approximate the first quantity by this one. And then we can the asymptotic variance of this the Greg estimator will be in fact the variance of the generalized difference estimator, which is easily computed. Now, the second approach is not supposing at all a model, and it is, in fact, based entirely on the sampling weights. In fact, as I said before, in a survey sampling point of view, the weights are very important, and every estimator is a weighted sum of, when you want to estimate a total, is a weighted sum of y variable. So now the goal is a little bit different. Deville and Sarandal in 92, they said that they wanted to build a new estimator, a weighted estimator, and to determine the weights that will be the closest possible, as close as possible to the sampling weight, which gives us the unbiased estimator, and satisfying what is called the calibration constraint. Namely, the estimator of the total of X by using these weights will give exactly the total that we know. And in fact, this equation is satisfied exactly whatever the sample is. It is something very, very strong, and I found it very magical in a way, because here you have an estimator, and it will be always equal to the true total. So we can use several distances, but we have to measure the closeness. But they have shown that we are asymptotically equivalent to the distance, to the weight obtained by what is called the chi-square distance given here. And in this situation, there is something, again, magical. We obtain the same weight, the same expression as the one derived by using a model-assisted approach. So in fact, for this distance, both approaches lead to the same estimator. Now, to obtain the asymptotic properties, we need to consider some asymptotic framework, which is a little bit contradictory with our situation when we suppose that population is finite. But in 92, Isaac and Fuller they said that we can consider as many populations that are of size larger and larger, going to infinity, and inside each population we consider a set of samples of size being also larger and larger. And we consider also some regularity condition about the first and second order inclusion probabilities on the second order of the variable and the auxiliary variable information. There are something that is really mild regularity condition. And in this situation, we can show, as I said before, that this reminder term is going to 0. And so we can approximate the variance of these two estimators. Just, I will go a little bit quickly. Now, what happens if the number of auxiliary covariates or auxiliary variable P is going larger and larger? Remember what I said at the beginning. If we consider, for example, the auxiliary information, the electricity consumption recorded every 30 minutes from the week before, we'll have enormous, a large number of auxiliary variable. And what happens in this situation? And if P is getting larger and larger and is comparable to the size of the sample. This is something that was already noticed in a classical regression modeling, where they have remarked that we have a problem of multicollinearity between covariables. The ordinary least square estimator has started to have a serious drawbacks, such as the large variance, or very in mean will be very far away from the real beta. And we can explain it by considering, we can explain it also by means of eigenvalues of the variance-covariance matrix of auxiliary variable. There are some, these are also already known results in a classical regression setting, but that can be used in a survey sampling to explain what happens in this situation. So it is a little bit surprising that in a survey sampling setting, the problem hasn't been remarked by means of a model, but by means of a calibration approach. As I said before, weights are very important for survey people. So they have remarked that when we have more and more calibration constraints, namely more and more variables for which we want to estimate exactly their total, the weights that we determine with the algorithm, with the optimization problem, they become to be more and more unstable. And they are very large and very far away from the sampling weights for which we want it to be very close. And finally, in 1997, they remarked by means of simulation that also considering many of auxiliary variables, the variance was larger and larger, while, remember, we wanted to build this estimator for improving the Orvis-Thompson estimator from the beginning. So something was happening on the number of variables was larger and larger. And just a little bit example to show you that what happens exactly. And we have the same electricity consumption curves from yes, the one considered at the beginning, but they are from the Ireland. And we want also for 1 week, and we want to estimate the electricity consumption of Monday of the second week. We consider a sample of 600, and we have all the auxiliary variables for the previous week, which are more than 300. So it is P is very large with respect to N. In this situation, just the curve, but they are the same as the one presented at the beginning. And now here, the first plot gives us the histogram of weights, of Gregg weights. If you can read the label, here we have from -40 to 60. They are very, very variable. And we can remark the same thing about the ratio with respect to the sampling design. So it is exactly what I told you. We can remark a large instability of weights when we have a large number of auxiliary variables. So something was happening when P is getting larger and larger, and this is why we wanted to see if we can express the asymptotic results with respect to P. Then now, which is supposed now to go to infinity also, when small n and capital N are going to infinity. And in fact, we have remarked, in fact, that except the first term, which is the difference, the generalized difference estimator, for which the error is not depending on P, is only depending, it is the usual consistency rate. All the terms are now depending on P, including for the beta coefficient. And more than that, the remainder term that we had for the Gregg estimator is depending on P with this consistency rate. This consistency rate will go to in probability to 0 with the good consistency rate if we have p, a number p of auxiliary variable that it respects this condition. Otherwise, this term will be also large, and in order to compute the variance of our estimator, it should be considered. So we have explained what people before remarked only by means of simulation. How to improve? We can see now that we have this term that is depending on p. We have some problem with weight. How can we improve this estimator based on a linear model with all p variables? So in classical statistical regression, there are two methods, two classes of methods. The one is based on penalization, just like lasso or ridge or with some other penalization method, or the dimension reduction method. So I will explain you quickly from both point of view. Maybe I will not have time to do all the presentation, but I'll do my best. So for the first, if we consider the model-assisted point of view, we need to estimate beta to obtain a better estimator of the regression coefficient that overcome the problem due to a large number of auxiliary variables. And a biased estimator of beta have been suggested in the 70s by Horrell and Kennard by considering this least square problem, optimization problem, plus a penalization, L2 penalization. Namely, we want the beta, the coefficient beta that optimize this objective function, but his square length is not very large. We can express in this way also. We have a closed formula that it is very like the OLS estimator, and for lambda here, the quantity lambda here, which is a tuning parameter, which will control the penalization. If we have lambda large, then we'll shrink the beta coefficient to 0. While when we are close to 0, if lambda is close to 0, we'll have large beta, which are closer to the OLS estimator. So it is a biased estimator that will be generally for lambda well chosen, will have lower mean square than the OLS estimator. So here is the second, is a constraint optimization problem. And in our survey sampling, we can use the same optimization problem, but here consider on the sample and with the weighted with the sampling weights. We will give also some kind an estimator, with a ridge type coefficient estimator. We'll have all over the S, the individuals only from the sample, and the sampling weights that are here on the diagonal. The estimator, if we plug in this new estimator of beta, we obtain a ridge type model-assisted estimator that again can be written as a weighted sum with weights that are not dependent on Y, but now are depending on the tuning parameter lambda. So, from a calibration point of view, remember the weights, we wanted to find weights that are as close as possible from this chi-square distance from the sampling weights. But now, because our weights were sometimes very large, some calibration equation were not very, was difficult to satisfy, then we don't ask anymore to be exactly satisfied. We allow a little difference with the known total. We don't ask that this quantity to be 0. Now we can allow some difference, to go some farther from the known total. And again, with lambda, in function of lambda, we can be close to the calibration estimator or close to the estimator, to the Orvis-Thompson estimator. So we can, it's something like a situation between the estimator that consider all the auxiliary information and the one that consider no auxiliary information. I will just skip this part, and we have studied the asymptotic properties of this ridge type estimator, and we obtain some consistency rate that now are depending also on P. And again, we can approximate the asymptotic variance of this new estimator with the variance of some kind of generalized estimator depending on lambda, only if P squared over N is going to 0. It is again the same condition. And finally, the second situation, the second method, in fact, which is based on reduction of the dimension. One method that it is very known, it is a principal component regression. We can also use in a survey sampling setting. So if we adopt the model-assisted point of view, we start with the model from the beginning, and now we just use a new parameterization of the regression function that can be written with respect to this new regression parameter, gamma. But now this new data matrix Z, called Z, has the property that the columns are orthogonal, and in fact that they are corresponding to what we call the principal component variable of the X matrix from the beginning. So people that are familiar with this principal component know the property of the principal components that are uncorrelated, of maximum variance and linear combination of the X variable from the beginning. So we can, these X variable in fact are ordered in function of their importance. The first one is the one that it is the most important. Its variance is the largest eigenvalues of the variance of X variables that have been centered in order to apply this method. And then one after the other one, they are ordered in function of their variance. So we can in fact just put away the last Z variable, which are corresponding to the lowest variance, and keep only the first R principal component with the highest variance. And the principal component estimator of beta is again a biased estimator, which consists of considering the part from the OLS estimator, the part that will belong to the R-dimensional space that will be spanned by the eigenvalues, the eigenvector corresponding to the largest eigenvalues with the largest variance, in fact. So we can see here that we can't compute this at the population level. We will estimate them with the same technique, and we obtain again some model-assisted estimator, where now we have weights that will depend on R, which is the new tuning parameter. R is the number of principal components that we keep in order to build our reduced, what is called a reduced model. In order to compute this estimator, we need to have the X for all the individuals from the population in order to compute the eigenvalues and the eigenvector of the matrix, of the variance matrix of X. If we don't have such information, we can estimate the eigenvalues with sampling designs, and then compute what is called the estimator of the principal components, and we can do again our method. if we have R equal to 0, we have the Orvis-Thompson estimator without auxiliary information, and the other, the opposite situation, when we have R equal to P, we have the classical Greg estimator from the beginning. Now, if we consider the asymptotic properties, now the consistency rate will depend on R, the number of kept variables, Z variable, which is generally we want to have R smaller, much smaller than N. So we have here a better consistency rate than the one obtained with Ridge, for example. And again, if R squared over N is going to 0, we can approximate the variance of this new Greg estimator based on principal components regression by the one that is based on the coefficient of beta computed at the population level. Again, a different kind of estimator. If we have a small empirical comparison always on Irish consumption data, just for example, our variables are highly correlated. The matrix is very conditioned. And for example, the first principal component at 1 explains more than 60% of total variance of X. And for example, the first 10 principal components, we have more than 80% of variance. So this can help us how to choose R in the number of components in practice. We want to estimate the total of electricity consumption of each date of the second week, of Monday, Tuesday, of all of the second weeks. And we select again a simple random sampling of size 600, and we compute the PC model-assisted estimator for increasing number R of PC variables. We want to see which is the impact of adding more and more principal components in our model. Here we have the coefficient of variation of the weights. We have on the simulation, we have more than 10,000 sample for each situation. And we start from here, we have only the first principal component, the most important, plus the intercept. Then we had the second one, and so on until the model with the full model with all the 336 variables. So here it is in fact which is the worst estimator. We have the estimator from the beginning with the full auxiliary information. So we can remark this. So as we add more and more variables, principal component variables in our model, the weights are more and more variable, and is here at the last with all variable, it is the worst situation. The box plot are larger and are higher with respect to the first one. Here also we consider the plot from left is for the complete auxiliary information. So we have the real eigenvalue and eigenvector, while at the right we have the one with estimated eigenvalue and estimated eigenvectors. We have also box plot of the proportion of positive weights, because with this kind of distance, we have a risk of having negative weights, and usually we don't have negative weights. So again, we start from one principal component, the most important one, to the 336 components, the complete model. And we can remark here that we don't have negative weights. And little by little, we have at the end, we have a large number here, a large proportion of negative weights. Again, when we have the complete model, when we have a large number of auxiliary variables, which are highly correlated among them. And the same phenomenon is remarked on the right. In fact, we don't have much difference between the real eigen elements and the estimated one. And again, and finally, just how we choose the tuning parameter are, I haven't spoken a lot, much on my talk. How we choose R or lambda for the ridge estimator. There is not a universal, we don't have a universal method. The one that we have used in our paper is the one suggested by one referee and also by suggested in this paper. In fact, we have chosen R or lambda such that all the weights in our sample were positive. So, and for these values, in fact, we have remarked that the results were very good. We have also computed the relative efficiency with respect to the Greg estimator, the one that considers all the auxiliary information, and for the values of the tuning parameters that obtain with this rule. We can remark here for all the days of the week that we have a great improvement. Here is the first one is the PC estimator, the ridge estimator, and the first line is the Orbis-Thomson estimator, the one that doesn't use auxiliary information. So we can remark that we have a real improvement with respect to the estimator that considers the whole set of correlated auxiliary information. And both methods are really are quite similar. We have the ratio is about between 0.4 to 0.555. So they are very good results. And but I don't know if I have much time or this is the last.
No problem, Professora. No problem.
Just quickly, the last. So when we have a lot of auxiliary variable, a lot of covariates, it is difficult. I have supposed here a linear model. In our situation, I haven't shown you, but when we want to plot to estimate the consumption of Monday, for example, with some historical consumption, very close historical consumption, the linear model is well adapted, but in other situations, maybe it's not so well adapted. And how, when we have a large dimension, just like here, it is not easy to see what kind of model we can use. So non-parametric models may be better in this situation. However, we know that when you have a large number of variables, the non-parametric models they have they are not working. The traditional non-parametric models are not working. So we can use, for example, some methods from machine learning, such as random forest or boosting, to estimate our total. And in this situation, even if the linear model was very well adapted, we have also tested if we have a random forest or XGBoost algorithm to estimate the regression function supposed to be non-linear. And we have remarked that, in fact, they give good estimation even in this situation where, as I said, the linear model was adapted. So just to I finish my talk on this some kind of opening question to how to use more general regression, non-parametric regression method and algorithm in this situation. How they are impacted by the number of auxiliary variables, which is going more and more larger and larger. And with Mehdi and David Aziza from University of Ottawa, we have studied their impact in another context. But there are a lot of many research interest that are still they are waiting still for response. So I will close my talk here. I think I was a little bit too. It was a little bit too large. too long. So thank you again for your attention, and I would be glad to answer to your question.
Thank you, Professor, for this great presentation. Now we have a moment to ask Professor Camelia questions.
Professor Camelia, what impact does applying to bootstrap criterion have on the selection of calibration variables in terms of reducing variability and variance inflation?
Sorry, I don't. Can you repeat? I am trying to put just to
Okay.
my okay.
What impact does applying the bootstrap criterion have on the selection of calibration variables in terms of reducing variability and variance inflation?
Okay, it's a good question, but I don't know. I haven't tried. Maybe, as I said, there are a lot of questions that they need to be answered. In fact, it's in a survey sampling setting. This question of high dimensionality, they are rather new. And why? Because until now, the survey, the national survey statistics, they didn't have very much auxiliary variables. It was usually of about 10, 15, something like that. And the problem didn't appear. And now they are starting having more and more variables. So research is getting the interest in this question the interest is larger and larger, but there are a lot of questions that had to be answered.
Okay, thank you.
Okay, any question?
Remember that you can make your question also raising your hand. And then we will give the permission to unmute your microphone. Okay, we have a question in Facebook. Question is, how does the incorporation of a higher number of calibration variables impact the variance of calibration estimator when dealing with high-dimensional auxiliary data sets in mathematical terms?
Yes, I haven't spoken at all about the variance. In fact, I'm trying to, it will impact also the variance estimation, but how it will impact, I don't know. I'm trying to see it, to start, because I already had this question, and also it interests me. For the moment, it was only for the total, but for the variance, I'm trying to look for it. I can't say you how much it is impacting, but what is the consistency rate? As this I can't tell you.
Okay, thank you very much. Our participant will appreciate your answer. Thank you very much.
Thank you. It's my pleasure.
Thank you, Professor. Thank you very much for your questions. We will continue in 1.5 hours, exactly 12:30 Colombia time and 6:30 p.m. Central European time. See you soon.
Thank you very much to all the participants for attending this conference.
Thank you very much for your question and the presentation for the Camellia, Professor Camellia. We will continue in 1.5 hours, 12:30 Colombia time and 6:30 p.m. Central European time. See you soon.
Va.
Hola, profesora, ¿cómo ha estado?
Muy bien. ¿Y usted?
Muy bien, gracias.
Yo no tengo la parte de atrás
No,
tan
no hay
bonita, ¿no?
se la hacemos llegar, se la hacemos llegar.
Vale,
Alessandra, por favor,
está muy bien.
por el chat de pronto la enviamos. Bueno,
Vale. Yo, ya mismo. La tengo, voy a verla. Me la bajo y me la pongo. A ver. Ujú. Vale, y vamos a ver aquí. Porque ahora que estáis, Alejandra, en un descanso. ¿Cómo? Ahora estáis en un descanso.
ya,
Sí,
ya.
estábamos en un break, pero ya vamos a retomar. Vale, muy bien. Voy a ver aquí. Y no soy capaz de ver en los puntos suspensivos, no me sale a mí.
Chat.
Eh, para cambiar el fondo, tienes que darle a las opciones de la cámara,
Ah,
donde
vale.
está la flechita de la cámara.
A ver.
Entonces le das seleccionar fondo virtual.
Aquí, míralo, vale. La verdad que no es un buen lugar para ponerlo, ¿eh? Entre nosotros. Oye, yo últimamente tengo unos pelos que cada vez que veo en un scroll digo, Dios mío, qué pelos
Está
tengo.
bien, profesor, está muy bien.
Ay, Dios mío. A ver, vale, voy aquí. Fondo y efectos. em, vale, y aquí fondos virtuales,
Ujú.
vídeo, avatar.
Añadir imagen o video.
Una pantalla, entonces ¿qué? A ver, video, mi video otra vez. Mi video, nada. Audio, nada, compartir fondo y efectos, pero en fondo y efectos no me deja. Ah, más, vale,
Sí,
aquí.
le
Añadir más.
colocas en más.
Vale, muy bien. Descargar y así estamos todos unificados.
Eso.
Gracias.
Muy bien, genial.
A ver, y creo que aquí hay un truco, mira, ya verás, ya verás. Retocar mi apariencia, veréis esto. Mira cómo me quita las arrugas.
Uy, qué bien.
Te digo, esto es un invento. Lo probé el otro día en el Zoom y es el único que lo tiene y es una maravilla.
No, genial. Está muy bueno,
Edith, te falta actualizar la tuya.
¿Así? Ah, carajo. Espera, a ver, yo miro.
A ver,
Profesora
ya verás que se nota
Macarena, ¿cómo
la diferencia.
está? Mucho gusto, profesora Macarena.
Igualmente, mucho gusto.
Gracias por aceptar la invitación de los organizadores.
Qué bien, me alegro mucho, muy feliz. Aquí hoy es la fiesta de cumpleaños de mi hija, entonces tengo que acabar súper en punto porque la tengo ahí como a la vuelta en plan, pero vamos
Felicitaciones.
muy bien de tiempo.
Sí.
Yo no sé vosotros cómo estáis allí, pero aquí estamos saturadísimos de tanto trabajo.
Sí, ya terminando año es un poco complicado, ¿no?
Terrible. Yo voy a dar una charla un poco especial. Espero que les guste.
Oh, será buena, seguro que sí.
Muchas
Bueno,
gracias.
muy práctica desde el punto de vista de la empresa.
Ah, muy bien. Esa es la idea aplicado. Bueno, hello everybody, welcome. We are happy to have you here today. Thank you. The next presentation will be in Spanish by Profesor Macarena Esteves. Profesora, ¿nos podría mostrar la presentación ahora
Voy.
mismo?
Por ello. Vale, pantalla. Un segundito, la tengo aquí abierta. Sí. Vale, y aquí. Aquí ya la veis, ¿verdad?
Ok.
Ajá, la pongo
Bien.
yo ahí.
Bueno, profesora, tiene 40 minutos para su presentación. Luego tendremos 10 minutos de preguntas, ¿ok?
Muy bien.
Puede comenzar, profesor.
Fenomenal. Bueno, pues nada, estoy súper contenta de estar aquí. He preparado un poquito una presentación con el día a día que yo vivo en las empresas y el tipo de cosas que se están haciendo ahora, sobre todo centrado en el área de marketing. Pero voy a haceros alguna pequeña introducción antes, ¿no? Porque todas las personas hablan de cómo se aplican las matemáticas en las empresas y muchas veces las personas pues se imaginan ahí como una cosa a veces como muy complicada o
Disculpe,
algo.
profesora, es que vamos a hacerle una introducción.
Ya
Ah,
decía yo, vale,
sí,
Exactamente, o sea,
entonces,
ahora,
disculpa.
no pasa nada.
bueno, es un gran honor para mí presentar a la profesora Macarena Esteves. Es matemática de la Universidad Autónoma de Madrid en España. Tiene una maestría en administración de empresas y es una experta profunda entusiasta de la ciencia de datos y el futuro de ella. Se desempeña como profesora en la Universidad Rey Juan Carlos, con una notable capacidad para clarificar conceptos abstractos y complejos. La profesora Macarena influye positivamente en los resultados empresariales. Anteriormente, la profesora Macarena ejerció como directora de la investigación en Mindshare, España y Latinoamérica. Ocupó cargos como profesora en el Departamento de Estadística y Econometría de la Universidad Carlos III de Madrid y en el máster en marketing de ESIC. Tiene diferentes premios, como lo es el Premio Internacional FIP Research Award al mejor trabajo de investigación publicado en 2011, entre muchos otros. En esta ocasión, la profesora Macarena presentará su charla titulada Matemáticas, Marketing e Inteligencia Artificial. Puede continuar, profesora.
Vale, fenomenal. Bueno, pues entonces, a mí me gusta explicar a las personas que normalmente, sobre todo en el área de marketing, cuando nosotros hablamos de matemática aplicada, pues hablamos de dos cosas. Muchas veces hablamos de contrastar hipótesis y otras veces de resolver problemas. Y es muy diferente el tipo de matemática que utilizamos cuando queremos contrastar hipótesis la matemática cuando queremos resolver problemas. En el caso de las matemáticas que utilizamos para contrastar hipótesis, que sobre todo son temas de estadística, ahora temas de machine learning, de deep learning, es muy importante la hipótesis a contrastar. Y esto os lo quiero contar porque sé que la mayoría de los que estáis escuchando sois estudiantes de matemáticas. Y muchas veces el matemático piensa que lo único y lo más importante es la matemática. Y es importante, pero también es muy importante entender el otro lado de la ecuación. O sea, las personas que están en un problema, que tienen una hipótesis, que quieren contrastar o que tienen un problema que quieren resolver, pues muy importante estar bien tener un conocimiento amplio de entender ese problema, ¿vale? Eso para que os recordéis. Bueno, si yo os presento, a cualquiera de vosotros os preguntara cuál de estas dos chicas es más guapa y cuando estamos en las empresas, pues cuando preguntamos cosas, muchas veces estamos en una situación como esta, que tú haces una pregunta y mucha gente va a decir una chica, otra gente va a decir otra chica, y entonces va a discutir y otro le va a dar razones. Pero si yo, por ejemplo, os pregunto ¿cuánto es 1 más 1? Entonces todos tenemos clara cuál es la respuesta. Esta es la situación que yo vivo cada día en las empresas cuando yo presento argumentos matemáticos. La matemática tiene la fortaleza de que es un argumento que en muchísimas ocasiones es difícil de rebatir. Y esta es la ventaja que tenemos nosotros, los matemáticos, que conocemos este idioma, que somos capaces de hablar este idioma. Pero acordaros siempre, sin olvidar que el idioma es importante y el que podamos pasar las cosas a un lenguaje matemático nos va a dar mucha fortaleza, pero que también es muy importante tener la humildad de saber que de otras cosas que los demás saben mucho, pues nosotros a lo mejor no sabemos tanto. Y que nosotros aprendamos esas cosas en los negocios, pues va a hacer que eso que nosotros vamos a aprender, más lo que ya sabemos de matemáticas, va a hacer que consigamos una solución más satisfactoria, ¿vale? Muy importante que os acordéis de esto. Bueno, yo os voy a hablar de temas de marketing, pero antes de eso quiero daros una introducción al concepto de futuro, ¿no? Porque es muy importante, o sea, yo creo para todos nosotros estamos viviendo ahora un momento en la historia de la humanidad muy importante porque todo está cambiando muy rápido. Entonces, cuando miramos hacia el futuro, cuando vosotros os planteéis un poco qué vais a hacer en vuestra carrera profesional, a qué os queréis dedicar, es muy importante que tengáis esa visión de largo fondo. Entonces, yo os voy a dar un consejo que es interesante y es que la clave de mirar al futuro no es mirar al futuro con los ojos de nuestro presente, sino que al futuro hay que mirarlo con los ojos de los niños que están por nacer. Esto es un tema muy importante. Cuando vosotros desarrolléis cosas en el futuro, cuando innovéis, cuando inventéis cosas, tenéis que siempre poneros en la piel de las personas que nacerán dentro de unos años, para los que esas cosas que nosotros hoy vamos a desarrollar serán su vida natural. Entonces, esto es importante, ¿por qué? Porque fijaros, nosotros por ahora, por ejemplo, ahora estamos desarrollando temas de realidad virtual. Entonces, la realidad virtual pues es una tecnología nueva que tú te la pones y puedes estar un rato viviendo una experiencia que, aun no siendo real físicamente, hace que tu cerebro la conciba como real. Entonces, muchas personas pues dicen, bueno, desarrollamos esta realidad virtual y no pasa nada porque, bueno, yo puedo estar un rato con estas gafas, pero luego sé que me voy a ir a dar al campo un paseo porque sé que pasear es una cosa muy buena para la salud y, y cuando yo concibo el futuro, pues lo estoy concibiendo pues porque para mí es importante la salud, porque para mí es importante estar con mi familia y esto es una cosa que la desarrollo ahora, pero que no va a ir a más, ¿no? Esto es un poco lo que muchas personas cuando conciben el futuro lo conciben desde su visión personal de su propia vida. ¿Cuál es la diferencia? Pues fijaros, ¿y cuál es el peligro de los desarrollos que se hacen para el futuro? Que nosotros en realidad estamos abriendo una puerta con esto que hoy os estoy contando, en este caso de la realidad virtual, pero que en el futuro los niños que todavía no han nacido y que entren por esa puerta van a entrar a un mundo que, aunque sea el mismo, lo vivirán de manera diferente. Esos niños que nazcan en el futuro y que para ellos el uso de la realidad virtual sea una cosa mucho más del día a día, mucho más natural, lo que para nosotros es virtual y además extraño, para ellos será virtual, pero casi os diría que será hasta real. ¿Vale? Entonces es muy importante cuando vosotros, y ahora todo lo que yo os voy a contar, cuando vosotros conceptualicéis el futuro, cuando vosotros estéis en las empresas, cuando vosotros construyáis el futuro, que siempre os acordéis que el futuro no es exactamente igual a lo que uno conceptualiza en el momento en que lo crea, sino que hay que intentar verlo cómo lo vivirán las personas que nacerán también en el futuro. Entonces, importante que sepáis hacia dónde caminamos nosotros, ¿vale? Cuando yo digo futuro, ¿qué podemos saber o qué podemos decir? Pues curiosamente, el futuro actualmente se define con un concepto matemático, que es el de singularidad tecnológica. Una singularidad, ya sabéis que es un concepto matemático. ¿Y por qué caminamos hacia una singularidad tecnológica? Pues fijaros, ¿qué tenemos en este gráfico? Tenemos en el eje horizontal el paso del tiempo y en el eje vertical la velocidad a la que avanza la tecnología. La curva está ajustada a datos reales desde 1950 y se ha demostrado que la manera en la que avanza la tecnología no es con una velocidad constante, sino que es con una velocidad acelerada. Y ya sabéis vosotros que la diferencia entre una velocidad constante, ta, 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 y una acelerada, ta, 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 ya sabéis que ese ta, 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 es una singularidad. Y eso es así. O sea, todo pronostica que esa curva se va a disparar al infinito. ¿Qué quiere eso decir? Nadie sabe muy bien lo que quiere decir. Lo que sí que sabemos bien es que a la par que eso está sucediendo, el ser humano no tiene la capacidad de convivir con un cambio demasiado acelerado. El cambio demasiado rápido resulta estresante al ser humano. ¿Y hacia dónde voy con todo esto? Pues fijaros, yo defiendo la siguiente teoría. Aquí tenemos otras dos curvas que la azul es parecida a la de la singularidad, pero es diferente. Es una curva que en el eje horizontal tiene el paso del tiempo y en el eje vertical tiene el grado de automatización de las tareas en las empresas. Y resulta que ahora lo que está pasando es que también el grado de automatización de las tareas en las empresas es acelerado. Es un poquito más, un poquito más, un poquito más, un poquito más. Y cada vez va a ser más la cantidad de máquinas que vamos a tener en las empresas haciendo cosas que ahora hacemos nosotros, entre otras muchas cosas matemáticas. Esa curva se combina con una curva naranja. Y la curva naranja no tiene nada que ver. La curva naranja tiene en el eje horizontal el tiempo y en el eje vertical el grado de saturación tecnológica que tenemos las personas. Y ahora estamos en el peor momento. Estamos en un momento de muchísima saturación. ¿Por qué estamos en ese momento? Pues porque nosotros venimos de generaciones en las que si no entendemos las cosas, si no las razonemos, si no sabemos cómo están las cosas hechas, no somos capaces no tenemos la suficiente confianza en las máquinas, porque tenemos esa necesidad de saberlo todo. Os lo digo porque es una cosa que a mí me pasa, ¿no? O sea, yo muchas veces trabajo con alumnos que vienen con soluciones que a lo mejor son mejores soluciones que las que tengo yo, pero que desconocen qué hay dentro de esa solución. Y a mí eso es una cosa que a mí particularmente me cuesta mucho. O sea, yo necesito entender, pero ¿qué va a pasar en el futuro? Pues lo que va a pasar es que a medida que las máquinas se van a ir metiendo más en las empresas, los jóvenes vais a ir entrando más en las empresas, con un grado de confianza mayor en las máquinas, eso va a hacer que el grado de saturación que tenemos las personas va a ir poquito a poquito desapareciendo. Y pienso que todo esto va a tener un equilibrio en el que en las empresas vamos a trabajar todos con las máquinas, con una confianza mayor en la máquina y con unas vidas más relajadas. Dicho esto, que es la introducción que os quería hacer, os voy a contar cosas que creo que son interesantes de la inteligencia artificial en marketing. El marketing, muchas veces los matemáticos, yo desemboqué en este mundo por casualidad. Nunca pensé que iba a trabajar en el mundo de marketing, porque el mundo de marketing, pues los matemáticos lo tenemos siempre como un mundo muy alejado. Sin embargo, es un mundo que está lleno de datos en tiempo real, de datos caóticos, cuando digo caóticos en el término matemático de la palabra, y datos que necesitan muchísimo de buenos matemáticos que estén detrás. Entonces, voy a empezar despacito. ¿Por qué hemos llegado a la situación en la que estamos? O sea, nosotros, ¿por qué necesitamos a las máquinas en las empresas? Pues fijaros, en las empresas siempre se han manejado muchos datos, pero ahora se manejan millones de datos. Si yo, por ejemplo, os digo, pues os voy a mandar unos datos que tenemos, pues, 200.000 filas y tenemos a lo mejor 50 columnas. Bueno, pues no me asusta. Es un conjunto de datos que de una u otra manera me voy a manejar. Cuando yo digo manejar, digo que casi que los voy a manejar con mis manitas, entendiendo bien todo lo que tengo en cada una de las columnas, cada una de las filas, viéndolo con los ojos. Pero cuando de repente me decís que a lo mejor tenemos 50 millones de datos, 50 millones de datos, entonces nosotros como seres humanos no tenemos la capacidad de manejar eso con nuestras manos. Cuando digo nuestras manos, digo nuestra mente. Por lo tanto, se abre una primera puerta a que necesitamos a las máquinas. Segunda puerta. Ahora cualquier cosa casi es un dato. Una imagen es un dato. Siempre ha sido así, pero nosotros como humanos no tenemos la capacidad mental de manejar las imágenes solos nosotros con nuestra cabeza como datos. No somos capaces de manejar los píxeles como datos. Necesitamos a las máquinas. Y la tercera puerta es el tiempo real. No que el dato llega en tiempo real, sino que el dato llega en tiempo real, el insight, el aprendizaje se produce en tiempo real y la acción por parte de la empresa tiene lugar en tiempo real. Entonces, tampoco somos nosotros capaces de estar ahí, porque somos incapaces, nosotros los seres humanos no somos capaces de manejarnos en tiempo real en las empresas, o sea, no somos capaces de tener suficiente número de seres humanos para que cuando una señora entra en un supermercado y esa señora es María López, que sabemos exactamente lo que le gusta o lo que puede comprar, no tenemos suficientes personas para que alguien vaya y le dé la mano y le diga, hola María López, mira, ¿te interesa? No, tenemos que usar la tecnología. Entonces, cuando nosotros llevamos eso a marketing, fijaros, nosotros vamos a evolucionar desde la relación humano-humano hasta la relación máquina-máquina. Y os voy a poner los ejemplos y vamos a hacer el recorrido. Humano-humano. Todavía funciona mucho humano-humano. Un director de marketing de una empresa quiere entender qué variables afectan a la venta de sus productos porque quiere hacer una predicción de sus ventas. Entonces, antiguamente y todavía, pues muchas veces habla con un analista, oye, que quiero hacer esta predicción, entonces el analista ve los datos, se va a trabajar y tarda unas semanas y a lo mejor en un mes o 2 meses le da las predicciones de las ventas. Ha evolucionado eso un poquito. ¿Por qué? Porque cuando ya el analista, pues a lo mejor ha hecho varias veces ese tipo de proyecciones, pues de repente pues habla con el desarrollador y hacen entre los dos una pequeña herramienta que ya pues es más fácil el director de marketing cuando quiere hacer una predicción puede ir a utilizar esa herramienta y puede hacer la predicción. Ahí el humano sigue siendo un poco el que dirige la acción. El paso de humano-máquina a máquina-humano, fijaros, es un paso muy fácil, pero que generalmente pocas empresas dan, les cuesta dar ese paso. ¿Y en qué consiste ese paso? Pues ese paso consiste en que en lugar de que el director de marketing tenga que ir a la herramienta, meterse, acordarse de cómo funcionaba la herramienta, preguntar a otro porque no se acuerda, tal. En vez de que pase todo eso, pues podemos parametrizar esa herramienta para que de manera más o menos inteligente, cuando suceda algo que realmente interese ver al director de marketing, automáticamente pues le puede mandar un mensaje comunicándoselo o diciendo que entre en la herramienta que hay algo interesante que pueda dar. Todavía no hay mucho ahí inteligencia artificial. ¿Qué es para mí inteligencia artificial y hacia dónde va el mundo? Pues fijaros, el mundo va hacia que una máquina sea capaz de hacer las predicciones de ventas de una compañía en tiempo real, que llegue ese dato a otra máquina en tiempo real que es capaz de estimar el pricing óptimo para enseñar a una persona en concreto, en unas condiciones concretas, dada esa predicción de ventas, para que se produzca la compra de un producto. Como veis, máquina habla con máquina, ¿vale? Este es un punto muy importante. ¿Por qué? Porque la clave del futuro de las compañías es esta. O sea, ¿cómo conceptualizo yo las compañías en el futuro? En el centro de las compañías tienen que estar las máquinas conectadas entre sí. ¿Por qué? Por lo que acabamos de explicar. Porque si yo tengo una máquina que es capaz de trabajar con millones de datos de cualquier tipo en tiempo real y esa máquina la conecto con un humano, No me sirve de nada tener esto, porque el humano no es capaz de manejarse ni con millones de datos ni de cualquier tipo ni en tiempo real. Así que las máquinas tienen que estar conectadas entre sí. ¿Dónde van a estar los humanos? Los humanos van a estar dirigiendo y definiendo la estrategia, no solo la estrategia de las compañías, la estrategia de precio, la estrategia de compras, la estrategia financiera, la estrategia de recursos humanos, un montón de humanos ahí. En el otro extremo, humanos pensando, inventando, innovando, desarrollando modelos. Y luego va a haber muchísimos seres humanos que lo que van a tener que estar haciendo, que ya lo hacen los humanos que trabajan en OpenAI, los creadores de ChatGPT, van a estar controlando que las máquinas estén funcionando bien, que las inteligencias artificiales no se estén equivocando. Porque os voy a contar otra cosa muy interesante, para que no la olvidéis nunca. Hay dos tipos de inteligencia artificial, no desde el punto de vista de lo que la inteligencia artificial es, sino desde el punto de vista de lo que la inteligencia artificial hace. Y os voy a contar la diferencia. Una es la inteligencia artificial industrial y la otra es la inteligencia artificial social. La inteligencia artificial industrial es la inteligencia artificial que desarrollamos y dejamos trabajando en las industrias. Desarrollas un algoritmo, lo pones a trabajar, te vas a tu casa, 2 años, ese algoritmo funciona fantásticamente. La inteligencia artificial social, que tiene la misma operativa que la otra, la diferencia es que es la inteligencia artificial que trabaja con los humanos al otro lado. Por ejemplo, los coches autónomos. ¿Y por qué se equivocan esas inteligencias artificiales? No porque estén mal construidas. Se equivocan porque los seres humanos somos erráticos. Y entonces es por eso que esas inteligencias artificiales, que van a ser la mayoría, inteligencias artificiales que al otro lado trabajan con seres humanos, tienen que tener un control exhaustivo y detallado de seres humanos, tanto para su desarrollo cuanto para su implementación, ¿vale? Importantísimo esto cuando la gente dice, no, vamos a perder el trabajo. No, los trabajos van a evolucionar, pero no los vamos a perder. Va a haber muchos nuevos trabajos. Bien, entonces, esto a lo mejor ya lo sabéis, pero os lo cuento porque es importante. Durante muchos años, hace como, pues, ¿qué os digo yo? Pues 6 o 7 años, nos hemos centrado los matemáticos mucho en el desarrollo de modelos. Todavía lo seguimos haciendo y es importante, pero es una cosa también que tenéis que saber, que aunque los modelos son súper importantes, esto es probado, esto que yo os digo, que dedicar mucho tiempo a mejorar un modelo suele ser en general menos productivo que dedicar mucho tiempo a trabajar bien los datos que alimentan el modelo. ¿Vale? Eso muchas veces es más entender bien el dato, pensar y poner inteligencia humana en ese dato, que pasar horas y horas y horas intentando mejorar un modelo. Vamos a tener mayor ganancia en el resultado si nos centramos en los datos. ¿Y qué quiere decir centrarnos en los datos? Pues quiere decir, nosotros tenemos todos los datos. Ventas, número de referencia, tamaño de las tiendas, precio. Y muchas veces vamos a meter estos datos en los modelos y vamos a ver qué soluciones tenemos. Pero imaginaros que luego vosotros un día estáis caminando por la calle. Si realmente estáis preocupados por un problema que tenéis en vuestra empresa, si realmente tenéis la vocación de resolver problemas en las empresas, vais a ir caminando por la calle y vais a estar pensando, este problema que tengo, no me acaba de convencer el modelo. He hecho un modelo, pero la cosa no acaba de estar bien, no es un modelo suficientemente robusto. Y entonces de repente vais a decir, ¿y si pruebo, en lugar de modelizar con la venta diaria, modelizar con la venta máxima en la última semana? Esto una máquina no lo puede hacer. Este tipo de ideas felices que tenemos los seres humanos, ideas geniales que tenemos los seres humanos, las máquinas no tienen esta capacidad. Y es muy importante que sepáis reconocer el valor de esto, porque es un poco lo que os decía, ¿no? Que la diferencia entre dos matemáticos brillantes la puede marcar el grado de creatividad que tenga uno de esos dos matemáticos. Y eso no va a venir de algoritmos de inteligencia artificial. Eso va a venir de vuestras propias cabezas. Entonces, ¿qué está sucediendo en las empresas? ¿Y qué le está sucediendo al departamento de marketing? Pues fijaros, a mí me gusta mucho, vosotros sabéis, me imagino que habréis escuchado, que muchas empresas están viviendo la transformación digital de sus compañías, ¿no? Porque han aparecido los nativos digitales, Amazon, Netflix, Uber. Estas empresas son empresas que han nacido ya en un ambiente totalmente digital y que tienen muchas ventajas de personalización de los datos, de datos en tiempo real, frente a las empresas de toda la vida. Entonces, las empresas de toda la vida, pues tienen que hacer esa transformación digital de su compañía. Y a mí me gusta poner el símil del cubo de Rubik porque les pasa un poco lo mismo a estas empresas, que ellos se gastan dinero y transforman una pieza de la compañía. ¿Qué sucede? Que cuando tú transformas una pieza de tu compañía, si esa pieza de tu compañía está en conexión con otra pieza que todavía no has podido transformar porque tienes que hacerlo todo con un tiempo y un plan, pues te da la sensación de que esto que ya has transformado no sirve para nada. Entonces, una compañía solamente va a tener su transformación digital finalizada cuando, como en el cubo de Rubik, todas las piezas tengan la posición correcta que tienen que tener, todas las piezas estén transformadas digitalmente y todas estén conectadas entre sí. A esto se une la realidad que estamos viviendo hoy en día, y es que por más que transformes todas las piezas de tu compañía, cuando llegues al final de tu pieza, ya la última que tenías que transformar, resulta que ya la primera que transformaste ya se te ha quedado anticuada. O sea que la realidad de las empresas de hoy en día es que es prácticamente imposible conseguir este cubo de Rubik, conseguir que todas tus piezas estén al día perfectamente transformadas en un mundo como el que estamos viviendo. Una de esas piezas es la pieza del departamento de marketing. Y una de las cosas que hacemos en las compañías con matemáticas y con inteligencia artificial es medir el retorno de las inversiones que hacemos en publicidad. Las empresas tienen diferentes partidas de dinero, ¿no? De gastos que hacen. Una de esas partidas, la más importante en cantidad, es lo que invierten en publicidad. Se gastan muchísimo dinero en publicidad. Y entonces les interesa mucho que lleguen matemáticos y les digan, oye, necesito que me digas si yo lo que me estoy gastando realmente me está generando un beneficio en mi empresa. Es una cosa súper, súper importante. Y te pueden decir, oye, necesito que me digas de lo que yo pienso, ¿no? O sea, me estoy gastando en televisión, me estoy gastando en radio, me estoy gastando en YouTube, me estoy gastando en Instagram, me estoy gastando en TikTok. Cada día me estoy gastando en más cosas, pues cómo me está funcionando esas inversiones, ¿no? Y una vez además me digas eso, me interesaría mucho si tú con las matemáticas me puedes decir si yo tengo 10 millones de euros, cómo yo tengo que repartir esos 10 millones de euros entre todos estos medios para maximizar mis ventas o para minimizar mi gasto, si tengo un objetivo de ventas determinado. Entonces, existen 3 tipos de enfoques ahora mismo en el mercado. El de arriba, que se llama Marketing Mix Modeling, es un enfoque estratégico. ¿Qué quiere decir con eso? Bueno, tú me vas a dar tus datos, me vas a dar el pasado de tus datos y yo lo que voy a hacer es un modelo, un modelo econométrico donde yo voy a meter todas las variables y yo te voy a decir cómo te está funcionando cada una de esas variables. Es un modelo donde yo te voy a decir cómo te funcionan los medios, también te voy a decir cómo te funciona el precio, porque como voy a modelizar las ventas de la compañía, tengo que meter como variables explicativas todas las variables que hay fuera. Aunque mi interés sea medir cómo funcionan los medios, si yo hay una variable que tú estás haciendo, por ejemplo, lo que hace tu competencia te afecta a tus ventas y tú no lo estás metiendo en el modelo ¿qué va a pensar? Pues va a pensar que lo que no le estás metiendo no existe, porque el modelo solamente concibe que existe algo que tú le estás metiendo. Entonces, si tú haces este tipo de modelos y no le incluyes todas las variables que realmente afectan a las ventas, el modelo, ¿le estás mintiendo tú? Pues él te va a mentir a ti también. Ese es un tipo de approach. Es un enfoque que es estratégico y que normalmente las compañías este tipo de análisis lo hacen una vez al año. Luego en el otro extremo tenemos una metodología que se llama Multitouch Attribution. ¿Veis que está en el otro extremo? Porque es en tiempo real, medición en tiempo real, y es una medición táctica. Es la clásica medición de atribución que se hace con los canales digitales. Google, Facebook, TikTok, Instagram, que tú hoy lanzas una campaña y en cuanto la lanzas ya estás viendo las personas que están respondiendo a tu campaña. Desde el punto de vista de la velocidad, son modelos muy útiles, pero no desde el punto de vista de, entre comillas, la verdad. ¿Por qué? Porque todo lo que sucede a nivel digital, pero la causa no siempre viene del mundo digital. El problema de medir las cosas en el mundo digital es que ignora la existencia del mundo físico. Entonces, es verdad que yo puedo estar navegando por Google, puedo ver una publicidad con un banner en un periódico de un producto telefónico y luego puedo hacer más cosas y por la tarde puedo estar en casa con mi hermano y mi hermano me puede comentar, oye, ¿viste que ha habido una oferta de esta compañía telefónica que es muy interesante? Y entonces yo puedo decir, pues mira, pues me lo voy a plantear. Y esa misma tarde voy a llamar a la compañía telefónica. La compañía telefónica seguramente va a atribuir mi llamada a el contacto que he tenido con el banner. Y sin embargo no es así. Entonces los modelos de atribución son útiles, muy demandados por las empresas, pero son modelos que hay que tener mucho cuidado porque no tienen no recogen todos los datos que existen en la realidad. Tanto los modelos de marketing mix modeling como los modelos de multitouch attribution, seguramente ya sabréis que los modelos econométricos en realidad lo que miden es correlación, no causalidad. Los diseños de experimentos, que seguro que también los conocéis, vienen del mundo de la química. Y a alguien se le ocurrió llevar el diseño de experimentos al mundo del marketing. ¿Qué sucede en la química? Pues que tú tienes un vasito, le pones una solución química, tienes otro vasito, le pones los mismos elementos, la misma solución, y si en este vasito echas una gota de azufre y estalla el vasito, pues sabemos que la causa del estallido ha sido la gota de azufre. Eso es un diseño de experimentos. ¿Qué hacemos en marketing cuando queremos causalidad? Queremos demostrar que la causa de que una persona haya comprado un producto ha sido haber visto mi anuncio. Pues creamos una especie de gemelos digitales, los llaman así, ¿no? Yo puedo, por ejemplo, Facebook, ¿qué hace? Pues Facebook te dice, mira, yo te voy a crear un grupo de personas y luego te voy a crear un grupo de personas gemelas. Y lo que voy a hacer es que a uno de estos grupos le voy a enseñar tu anuncio y al otro no. Y luego vamos a ver cuántos de estos de aquí compran tu producto y de estos a ver cuánto lo compran. ¿Qué sucede? Pues a los anunciantes les gusta el hecho de decir, bueno, efectivamente esto es, no hay tu tía, o sea, aquí esto es causa-efecto. Pero ¿cuál es el problema de los diseños de experimentos? Pues el problema es que tiene dos problemas. Uno, que cada diseño de experimentos solo puedes medir una cosa. Y dos, que hablar de conjuntos gemelos en algo que no es la química, pues generalmente no es del todo correcto. No es del todo correcto. Nunca es igual. Y entonces, me diréis, pero Maca, entonces ninguno de los tres vale, o los tres valen. Bueno, es así. O sea, tenéis que saber que cuando lleguéis al mundo de la empresa, el mundo de la empresa no es perfecto, no es como los estudios, que en los estudios pues estudias las cosas y haces los problemas y los resuelves. No, el mundo de la empresa está lleno de circunstancias y de personas que viven experiencias y cosas que el matemático tiene que intentar adaptarse a eso. Eso es muy importante porque los matemáticos cuando llegamos al mundo de la empresa tenemos un choque. El choque de decir, pero un momento, si 1 más 1 son 2, aquí porque sale 2,3. O sea, exagerando un poco el tema. Pero tú llegas al mundo de la empresa y veis cosas como este que yo os estoy contando, que todo es un poquito imperfecto. Y nada es perfecto como son las matemáticas. ¿Vale? Pero por otra parte, es apasionante. Y es apasionante ver cómo podemos ayudar a las personas en las empresas a conseguir demostrar sus teorías, a conseguir resolver sus problemas. Es de verdad, es apasionante y el mundo del marketing en particular es apasionante. Bueno, entonces, fijaros, una de las cosas que que yo siempre digo cuando hablo con mis clientes es que la matemática es un lenguaje paralelo al lenguaje habitual que nosotros hablamos. Y yo siempre les digo, si tú me cuentas una historia y me das unos datos, yo te voy a poner esa historia en lenguaje matemático. ¿Qué ventaja tiene? Pues que con esa historia yo voy a poder cuantificar las cosas y voy a poder demostrar relaciones entre variables. Y eso es maravilloso, ¿no? Porque yo le puedo decir, oye, yo creo que la televisión funciona. O te puedo decir, yo te he demostrado que cuando tú inviertes 10.000 euros en una campaña de televisión, tus ventas incrementan un 2%. No tiene nada que ver una cosa con la otra. Entonces, ¿qué tengo aquí? Cuando nosotros hacemos un modelo en marketing, por ejemplo, un modelo como el que os he explicado de ROI, nosotros tenemos que tener claro todo lo que puede suceder en torno al anunciante con el que estemos trabajando. ¿Y qué tengo yo aquí delante? Yo tengo la representación gráfica de un conjunto de ecuaciones que reflejan el marco teórico sobre el que se sustenta mi cliente. Y este marco teórico dice lo siguiente. Este es un anunciante que tiene un canal de ventas offline y un canal de ventas online. Cuando yo hago medios tradicionales, cuando hago una campaña de publicidad, hay gente que ve la campaña, va a la tienda física y compra. Pero también hay gente que ve la campaña, hace una búsqueda en Google, visita la página web y hay gente que compra en la página web, pero también hay gente que después de visitar la página web va a la tienda física y compra. Y luego veis un montón de cosas más. ¿Qué tengo aquí? Un sistema de 4 ecuaciones. La explicación de las ventas offline, la explicación de las búsquedas, la explicación de las visitas a la web y la explicación de las ventas online. 4 ecuaciones con un montón de variables relacionadas entre sí. ¿Y cuál es nuestro objetivo como matemáticos? Resolver esta ecuación. Y con eso vamos a ayudar al anunciante a resolver un montón de preguntas. Entonces, por ejemplo, vamos a pensar en el caso de que tengamos una campaña de televisión. Fijaros, tú puedes decir, oye, vale, yo te voy a mostrar que cuando tú haces una campaña de televisión, tú, la semana en la que haces la campaña, tienes un incremento en ventas. Efecto en el corto plazo. Pero luego el matemático que piensa, va por la calle paseando y dice, es verdad que yo tengo ese efecto, que yo esta semana pongo un anuncio y luego tengo un incremento. Las marcas durante mucho tiempo hacen publicidad. Y muchas veces cuando yo tengo una serie de ventas y tengo un modelo econométrico, tengo una constante, ventas igual a alfa, y esa constante es muy importante. Y no me da información, porque alfa no me da información, solamente es un número, pero no me da opción a yo poder hacer más grande o más pequeño ese número. Y eso puede ser. Eso no puede ser. O sea, no puede ser que un anunciante que vende mucho tenga ahí una variable que sea totalmente constante. Y sin embargo, porque tú dices, ¿y por qué vende mucho ese anunciante? Pues porque tiene una marca muy conocida. ¿Y por qué tiene una marca muy conocida? Porque durante mucho tiempo, muchos años, ha ido haciendo mucha publicidad. Y entonces se te puede ocurrir decir, bueno, pues voy a transformar la suma de toda la publicidad a lo largo del tiempo y voy a utilizar eso como una medición en el largo plazo de todo lo que ha hecho esa marca y eso va a ser también un efecto en el largo plazo en la publicidad. Y además acabamos de ver que yo puedo tener una campaña de televisión y puedo notar un efecto en ventas. Tengo una campaña en Google y noto un efecto en ventas, pero es que resulta que cuando yo tengo la campaña de televisión, eso hace que las búsquedas en Google crezcan y por lo tanto tengo un efecto directo de la tele, pero también indirecto a través de mejorar el ratio de Google. También puedo tener 2 productos. Yo puedo ser una empresa que vende yogures y que vende pizzas. Y puedo hacer una campaña de yogures y como la marca es común, puedo tener un efecto halo sobre las pizzas. Y también puedo decir, oye, puede que tú haces tele y tienes un efecto. Haces radio y tienes un efecto. Pero cuando haces tele y radio juntas, tiene un efecto extra también. El matemático tiene que tener 2 virtudes, chicos. 2 virtudes. Una, ser capaz de pensar, porque muchas veces a las personas, al de negocio, no se le ocurren estas cosas. Tú tienes que tener la virtud como matemático de escuchar y ser capaz de, viendo lo que ellos dicen, escuchando de lo que hablan, tener tú ideas que luego puedas convertir en realidad. Que tú digas, es verdad, cuando tú inviertes en tele tienes un efecto. Cuando inviertes en radio tienes un efecto, pero cuando inviertes en tele y en radio puedes tener otro efecto extra. ¿Qué tengo que hacer ahí? Sumar tele multiplicada por radio. Ese es el valor del matemático. Decir, vale, ¿y esto cómo lo voy a hacer? Ah, pues esto lo voy a hacer así. Pues esto voy a hacer, esto dividido por esto, y lo voy a hacer de esta manera. Y esa es la creatividad del matemático. Como en los exámenes, cuando se cae un problema que es difícil, que no es el problema que vas a resolver con todo lo que estudiaste, sino con lo que de repente se te ocurrió. Ahora os voy a contar dos cosas más. En el mundo, ahí tengo que correr, pero bueno, solamente que sepáis, en el mundo de la publicidad hay poca ciencia, pero hay dos cosas que son ciencia. Una es esta, que dice que cuando tú haces un anuncio, tú tienes un efecto, quitas el anuncio, desaparece el efecto, eso cuando es una promoción. Pero en el caso de la publicidad, ese efecto no desaparece. Es una cosa que se denomina el concepto de ad stock. Cuando tú tienes hoy una campaña, tienes un efecto. Y mañana no tienes campaña, pero queda un efecto todavía de lo que has hecho. Y eso tienes que medirlo matemáticamente. La siguiente cosa que es ciencia en la publicidad es que la relación que hay entre lo que tú inviertes y lo que tú ganas no es lineal. Tiene esta forma que es de retornos decrecientes. ¿Por qué? Porque cuando tú vas metiendo dinero en los medios, lo que vas haciendo es conseguir que la gente vea tu anuncio. Pero llega un momento en que por mucho más dinero que metas en un medio, ya no hay más gente a la que impactar, porque ya todo el mundo que está en ese medio ya te vio. Entonces, si metes más dinero, lo que vas a hacer es sencillamente que el que te vio una vez te va a ver 16 veces. Y porque te vea 16 veces no va a comprar más tu producto. Así que la relación entre lo que inviertes y lo que vendes es de retornos decrecientes. Llega un momento que ya no vas a crecer más en venta. Y decirle a tu anunciante qué punto de inversión es ese es una cosa que se valora mucho en marketing. Entonces, corro para que me podáis hacer preguntitas. Entonces, más cosas que tenéis que saber. La marca. La marca es un valor intangible. Los valores intangibles tienen una característica muy importante. ¿Perdón?
Disculpa,
No,
tómate tu tiempo.
vale, bueno, es que,
Estamos
pero que
llegando.
tampoco luego me puedo quedar yo mucho tiempo. Pero bueno, lo más importante os lo voy a enseñar.
Vale.
Esto es muy importante que lo sepáis. Mirad, modelos estructurales. No sé si los habéis estudiado, pero si no los habéis estudiado y algún día os encontráis con alguien que os dice, oye, quiero medir esto, que es un valor intangible. ¿Qué es un valor intangible? Un valor intangible es una métrica en las empresas que no se puede tangibilizar, no es como cuántos kilos he vendido, a qué precio he puesto mi producto, sino, oye, ¿cuánto vale mi marca? ¿Cuál es el valor de mi marca? ¿Cuál es la reputación de mi compañía? Entonces, estas variables se llaman intangibles y tienen una característica que es que tú, cuando tú preguntas a las personas cuál es el valor de una marca, tú no puedes preguntar por el valor en sí, porque nadie sabe cuánto vale una marca. Si yo os digo, oye, valorarme de 0 a 10 la marca Coca-Cola, cada uno de vosotros me va a dar un número, pero ¿qué hay detrás de ese número? Entonces, tenéis que aprender dos cosas. Los valores intangibles son muy importantes para las compañías. No se pueden medir con una sola pregunta. Tienes que ver en academia, hay mucha gente que ha estudiado esto, tienes que ver cuál es el constructo, cómo tienes tú que preguntar para que cuando tú sabiendo cómo han respondido a muchas preguntas, puedes ver cuál es el valor de la marca. Y los modelos estructurales trabajan con una cosa que son las variables latentes, que son variables que tú no preguntas por ellas, pero inferes el valor que tiene la variable con una serie de modelos de gestión que base a cómo la persona se hace esas preguntas. Entonces, importante que sepáis eso, que sepáis que estos valores intangibles son importantes, normalmente estudian con una investigación que es secundaria. Y muchas personas que dicen, pero yo no quiero hacer esta investigación, yo quiero usar las redes sociales, ver lo que la gente dice en las redes sociales de mi marca. No, qué barbaridad. No, eso no se puede hacer. ¿Por qué? Por lo que os acabo de explicar. Porque una marca no es lo que la gente dice en las redes sociales, no. Una marca tiene un constructo, tiene una parte de contenido de producto, tiene otra parte de contenido social, tiene otra parte de contenido de los empleados. Lo que sí se puede hacer es cuando tú tienes una buena métrica construida con un buen modelo matemático, sí que puedes utilizar la vivencia, el tiempo real de las redes sociales para calibrar si más o menos esa medida puede estar bajando o subiendo, ¿vale? Importante que os acordéis. Otro mundo apasionante para que estén los matemáticos trabajando. Luego, temas de los clientes. Mil cosas aquí. Por ejemplo, los clientes se segmentan. ¿Cuántos tipos de clientes tenemos? 8, 5. Ahora, ¿qué se está haciendo con la inteligencia artificial? Se está intentando tener segmentaciones de clientes en tiempo real. ¿Por qué? Porque la vida cambia de un día para otro. Entonces, eso de decir, yo tengo 8 tipos de clientes, hombre, pues ahora mismo eso es una cosa que ya nadie se cree. ¿Por qué? Porque lo que tú tienes hoy ya es distinto de lo que tenías ayer. Entonces, todos los temas, por ejemplo, de las tiendas que tienes, de cómo te están funcionando, todo lo que es cliente tiene muchísimos temas de inteligencia artificial. Luego, por ejemplo, más cosas interesantes que quiero comer. Por ejemplo, inteligencia artificial en la última milla. Esto es lo que os contaba antes de la señora, que entra en una tienda y según entra en la tienda tienes enfrente una pantalla y la pantalla tiene un mensaje que es personalizado para esa persona. ¿Vale? Eso es lo que se dice el marketing en la última milla. En el momento en el que una persona va a hacer una compra, tener la capacidad de impactar con publicidad a esas personas en ese momento, con una campaña personalizada. ¿Vale? Esto ahora se puede hacer porque, por ejemplo, ahora se pueden comprar los datos de las señales de los teléfonos móviles. También, por ejemplo, el dato de las IPs de los hogares es un dato que está disponible, que es un dato gratuito. Entonces, nosotros, por ejemplo, pues podemos saber qué televisión conectada se consume en los hogares, sin que las personas sepan que se sabe, eso se sabe. Y puedes saber por dónde se han movido las personas en un día. Y sabiendo por dónde se ha movido la persona, sabes cómo es la persona, porque si la persona ha ido en el último mes 2 veces a 2 conciertos, pues sabes que les gustan los conciertos. Entonces, el mundo del dato y el mundo del tiempo real está lleno de números, lleno de modelos y deseoso de contratar matemáticos. En este punto de la última milla, una de las cosas que más se está ahora desarrollando es todo el tema del Edge Machine Learning, que es que no tener que ir a la nube. O sea, porque esta persona entra en el supermercado, entonces en el momento en el que entra en el supermercado, el dispositivo sabe quién es la persona, manda la señal, ¿vale? De, por ejemplo, la imagen de la cara de la señora, manda la imagen a la nube y de la nube baja el dato que queramos que baje. Entonces, eso supone tiempo y supone también energía, ¿no? Y entonces una de las cosas que se está haciendo mucho ahora es intentar desarrollar que parte de los algoritmos de Machine Learning estén en los propios dispositivos, ¿vale? Esto es también interesante que lo conozcáis. Otro tema muy interesante, pricing dinámico. Pricing dinámico, pues tiene que ver, pues eso, ¿no? Que en vez de decir que las cosas cuesten lo que me han costado a mí y le pongo un margen, no, que el precio de las cosas sea cuánto es el valor para ti de esa cosa. Como hacemos con los billetes de avión ya hace muchos años. Pues eso te preguntas, ¿y por qué no se hace en más cosas? Cada vez se hace en más cosas porque las empresas ganan mucho más dinero si lo hacen así que si lo hacen de la otra manera. Entonces, todo eso está lleno de algoritmos matemáticos para maximizar los ingresos y para maximizar la probabilidad de compra. Y esto es una cosa que tiene que ser que, vamos, yo siempre digo que tendría que ir mucho más rápido de lo que va. Luego, por ejemplo, pues también en temas de pricing, las empresas, por ejemplo, pensar en todas las empresas que venden sus productos en supermercados. Esas empresas normalmente no saben el precio al que se vende su producto. Saben el precio al que han vendido ellos su producto a la empresa mayorista. Pero luego la empresa mayorista tiene sus propios precios y sus propios descuentos. Entonces, eso, por ejemplo, ahora mismo con la inteligencia artificial debería de ser de otra manera. O sea, los anunciantes deberían de tener un control mucho más directo y exhaustivo y preciso del precio al que se están vendiendo sus productos. Luego, más cosas que seguro que conocéis, todos los temas de generación de contenidos en tiempo real. Esto ya con las IAs generativas. Pues esto está creciendo muchísimo. Este ejemplo que yo os voy a poner es un ejemplo de hace años de tener este banner y con datos de Facebook hacer una clusterización, determinar 8 tipos de diferentes personas interesadas por los zapatos y poder customizar las creatividades para cada una de esas personas. Esto ahora se hace de manera súper fácil. Vale, entonces, solamente para cerrar ya, ¿a quién están contratando los departamentos de marketing? ¿Quién va a estar en los departamentos de marketing en el futuro? Ahora mismo en las empresas en general tenemos 3 tipos de perfiles. Los perfiles muy específicos. Cuando yo empecé a trabajar, yo soy matemática, a mí me contrató una compañía y yo hacía todo. Ahora eso ya no es así. O sea, tú ahora contratas a un matemático, pero el matemático no puede hacerlo todo, porque es que ahora es que hay que hacer 1000 cosas. Ahora tienes que saber puedes saber de Machine Learning, pero no es lo mismo que sepas de Deep Learning. Dentro de Deep Learning hay gente que tiene que ser específica de un tipo de redes neuronales, o la gente que trabaja con NLP. O sea, ahora necesitamos muchos expertos en diferentes áreas dentro de la parte científica. Luego tenemos muchos perfiles que son perfiles que no habiendo estudiado matemáticas o ingeniería, son perfiles que han hecho carreras más de humanidades, empresariales, a lo mejor una economía, psicología, pero que la complementan con másters o estudios posteriores en temas más de ciencia de datos. Son perfiles que se están colocando muy bien en las empresas porque tienen unas soft skills interesantes y también saben suficiente para manejándose con las máquinas resolver problemas complicados. Y luego tenemos los otros. ¿Y quiénes son los otros? Los otros son lo que va a estar en el futuro en las empresas, que son los ciudadanos científicos de datos, que es cualquier persona que lo que va a hacer es trabajar con las máquinas exactamente igual que vamos en el coche con el GPS. ¿Quién de vosotros conoce cuál es el algoritmo del GPS de vuestro coche? Nadie. ¿Todas las personas se manejan con el GPS? ¿Todas las personas confían en el GPS? Sí, perfectamente. Pues lo mismo va a pasar en el futuro con los algoritmos y las máquinas en las empresas. La gente va a optimizar, la gente va a predecir, la gente va a segmentar sin necesariamente tener que saber eso cómo se hace. Entonces, ya cerrando solamente, ventajas de hacer las cosas con Data Science. Subimos una montaña con nuestras piernas. Conocemos todos los recovecos. Tenemos esa seguridad. ¿Cuántas montañas somos capaces de subir en una semana? Una montaña. Machine Learning. ¿Cuántas montañas? Los que queramos. En 2 minutos. ¿Qué sabemos de la montaña? Nada. ¿Pero subimos 25 cimas? Podemos subir 25 cimas. Ahora mismo está la cosa entre una y otra. Y ya la última diapositiva, sencillamente, ventajas de la inteligencia artificial. ¿Por qué las empresas quieren llevar la inteligencia artificial al marketing, a todas sus áreas? Por la velocidad de tener acceso a todo, la reducción de costes, reducción de complejidad, las nuevas formas de compromiso, más innovación, mayor confianza. O sea, son muchas las ventajas para las empresas. Bueno, y con esto, dejo para que tengáis un para decirme nada. Bueno, sí, tenemos 10 minutitos. Está bien. Yo no te escucho.
¿Ya me escuchan?
Sí.
Ok. Decía que muchas gracias, profesora Macarena, por su presentación. Muy interesante. Es-
¿Los chicos suelen hacer preguntas o no? Yo no les veo.
Sí,
Voy a ver.
en el chat hay participantes, en el chat hay una pregunta. Julián L., no sé si él quiera decirla o la leo. Es, ¿qué es más viable o efectivo o rápido en cuanto al desempeño óptimo en lectura de mercado? ¿Migrar un matemático al mundo de los negocios o alguien del mundo de los negocios con buena aptitud matemática?
Pues mira, qué bonita pregunta y qué interesante. A ver, todo el mundo se mata por los matemáticos, pero te digo, los matemáticos luego somos como somos. Entonces, muchas veces tú coges el matemático, pero si luego el matemático no es capaz de adaptarse. Por ejemplo, yo toda mi vida he tenido empresas de matemáticos y he tenido matemáticos que no podían hablar delante de un cliente, porque si hablaban delante de un cliente, el cliente no entendía nada. Entonces, yo, por ejemplo, en esos casos, he preferido un peor matemático, pero con más capacidad de entender lo que el cliente necesita y de dar una solución a su cliente. Eso es importante que lo sepáis. Lo mejor es ser un brillante matemático, pero que tenga la capacidad de explicar, primero, que tenga la capacidad de escuchar cuál es tu problema. Tengo verdaderamente interés en conocer el problema de este cliente. Escuchar. Luego pensar, disfrutar con las matemáticas. Y luego ser capaz de contar la solución matemática para que la entiendan y la implementen. Y realmente ver que lo que tú haces ha servido para algo. Eso es súper importante. Pero te digo, sigue siendo hoy en día que muchas empresas están contratando a los matemáticos porque hay muchos problemas muy difíciles de resolver. Y ahí es verdad que el matemático, pues lógicamente tiene una mente distinta que el que ha hecho 5 años de una carrera empresarial y luego ha hecho a lo mejor 6 meses de un máster en Data Science. Gracias por la pregunta.
Esta pregunta, Lina Herrera nos pregunta, buenas tardes, profesora Macarena. ¿Cómo un químico cabe dentro del mundo del marketing y de la adaptación de la inteligencia artificial en las compañías?
Vale. Lo bueno que tiene el marketing es que aunque no lo estudiemos, lo vivimos todos los días. Todos los días vivimos ver publicidad, vivimos tener precios, comprar, no comprar, vivimos el mundo digital. Entonces, el marketing tiene eso de bonito, de divertido, que lo que haces en el marketing es lo que vives en tu día a día. También tiene divertido que algunas veces trabajas para coches, otras veces trabajas para yogures, otras veces trabajas para energéticas. Entonces, eso también es divertido, que puedes estar desarrollando modelos para diferentes anunciantes y tiene esa variedad. Un químico tiene un aprendizaje bastante científico y por lo tanto tiene una mente con capacidad científica y eso tiene un valor. Yo he conocido gente, licenciados en químicas, he tenido una de mis manos derechas en mi empresa, era una doctora en ciencias químicas, una mujer brillante, con una capacidad de razonar y de pensar brillante. Entonces, ser químico ya es una buena credencial. Y en marketing entra cualquiera. O sea, es que en marketing abre las puertas a cualquier talento matemático.
Súper bien. ¿Hay más preguntas?
Bueno, yo quisiera hacer un par de preguntas a la profesora Macarena. Es que en verdad me ha parecido muy, muy increíble, digamos, la presentación. Entonces, desde ICMM Latinoamérica, como una organización de matemáticos, nosotros estamos comprometidos, ¿verdad?, con trabajar en la visibilización digamos, de nuestro talento joven en Latinoamérica y mostrarlo en otros escenarios, ¿verdad? Entonces, profesora, de acuerdo a su experiencia, ¿cómo nosotros podemos usar el marketing o apropiarnos de estas herramientas, digamos, de acuerdo a su percepción personal, para encaminar esos objetivos? Esa es una pregunta un tanto encaminada hacia nuestra organización, ¿verdad? Que no me resisto, pues, por hacerlo. La primera.
Bueno, perfecto. O sea, eso se puede hacer. O sea, al final, tu objetivo ¿cuál es? Que la gente os conozca y que la gente conozca vuestros matemáticos y el valor. Para hacer eso, tienes que hablar con gente experta que sabe hacer eso. Y luego tienes que medir que realmente lo que estés haciendo te está dando valor. Eso lo vamos a hacer con los modelos matemáticos. Pero yo te animo muchísimo. En España, ahora, porque antiguamente era difícil salir de tu país, pero ahora los americanos, los europeos, Están contratando matemáticos en todo el mundo. Tú ahora puedes estar en tu casa y trabajar para una empresa americana o una empresa española siendo matemático. Y todo eso, luego si quieres hablamos, Duván, y yo os echo una mano en lo que haga falta.
Muchas gracias. Y una segunda pregunta, digamos, más encaminada, digamos, a esos jóvenes latinoamericanos que están en sus casas en este momento, que están en su celular, mirando tu conferencia. ¿Qué mensaje les darías tú? ¿Qué palabras puedes compartirles a ellos para que enriquezcan digamos, su carrera o su camino en torno, pues, a tu experiencia profesional con el marketing y las matemáticas y las comunicaciones, etcétera?
Bueno, yo les diría, qué suerte haber estudiado matemáticas. O sea, yo estudié matemáticas por casualidad. Y cuando yo pienso el día que me muera, que yo me voy a llevar, una de las cosas que yo me voy a llevar el día que me muera es haber estudiado matemáticas. Porque cuando estudias matemáticas, sin darte cuenta, tu mente se estructura de una manera distinta. Y eso hace que cuando seas mayor y te enfrentas a los problemas de las empresas, tienes una manera de mirarlos distinta que es apasionante, te hace diferente y poderoso. Dicho esto, la humildad es fundamental. El matemático tiene que ser humilde y tiene que saber escuchar y tiene que saber apasionarse con sus problemas. A veces veo matemáticos que no les importa lo que el cliente piensa o el problema que tiene el cliente, no. Realmente lo importante es solucionar problemas, no es crear un algoritmo que es nuevo, no, es solucionar el problema, lo solucioné. Pero bueno, sobre todo le diría eso, que qué suerte que han estudiado matemáticas. Ya sí que
Muchas
me tengo que
gracias.
ir, que si no mi hija me va a matar.
Hay una pregunta en el chat, una última pregunta, creo.
Venga, dale.
Miguel Fernández Pérez dice, ¿es más conveniente codificar variables como binarias haciendo categorías o como continuas para
Esa
problemas de
pregunta la vi.
marketing
Hombre, a mí dame
o
variables
dar,
continuas. Yo sí, continua
o,
mejor.
o dar
Mejor continua.
recomendaciones para codificar variables? Dice.
Sí, mejor variable. O sea, al final una variable continua te da más información. La variable binaria te da menos información. Pero bueno, hay técnicas para las variables binarias, o sea que tampoco pasa nada. Pero yo particularmente prefiero las continuas. Cualquier cosa que me conectéis por redes sociales, que encantadísima de ayudar a matemáticos del mundo.
Muchas gracias, Macarena.
Besitos
Estés
desde
muy
España.
bien.
Muchas
Adiós,
gracias.
chao.
Vale, adiós. Duan.
Ok, muy bien. Después de escuchar esta conferencia tan interesante sobre las aplicaciones de las matemáticas en el mundo del marketing, eh, estaremos iniciando en media hora con la charla del profesor Senapatis, del profesor Bisbaraham. So, to all the participants that are connected in Europe, we are going to start more or less in 30 minutes our scientific program with Professor Senapati. Hello everyone. Hola a todos los participantes que nos están escuchando. En este momento tenemos una pausa aproximadamente de 20 minutos antes de iniciar la prueba de la charla del profesor Isbarahan Senapati, pero nos encantaría escucharlos a ustedes, nos encantaría escuchar quién está al otro lado de la pantalla. Entonces, los invitamos en este momento, más o menos a una charla de 10 minutos y que nos cuenten de qué parte de Latinoamérica se están conectando.
Pueden activar su audio a partir de este momento, si quieren.
Buenas tardes.
Buenas tardes.
¿Qué tal? Me pareció buenísima la charla de la señora Macarena. Yo soy profesora de matemáticas en Nicaragua.
Sí, puedes activar tu video si quieres.
¿Sí? ¿Está bien?
Laureana, ¿cómo
Sí.
estás?
Sí, estoy muy contenta de poder estar en estas conferencias. De verdad que están muy interesantes todas
Sí,
y me ha encantado, digamos, poder compartir, digamos, esta mañana con varios conferencistas, ¿verdad? Estoy en Nicaragua, en León, en la Universidad Nacional Autónoma de Nicaragua, en la Universidad de León.
muchas gracias, Laureana.
Sí,
Muchas
mucho
gracias por
gusto.
conectarte. Mucho
Y
gusto.
felicidades por esa organización del evento.
Muchas
Aquí,
gracias.
desde ICMAM, estamos para servirles.
Gracias.
Bueno, también nos escriben en el chat que están desde Chile, desde la Universidad Santiago de Chile y desde la Universidad Técnica de Federico Santa María.
Carlos,
Muy
¿cómo
buenas,
estás?
¿cómo están? Muy buenas tardes. Muy agradecido primeramente por haberme admitido en estas charlas tan interesantes. La doctora Macarena ha dado una excelente ponencia. Le estoy hablando desde Perú, Ica. Yo soy docente de la Universidad Nacional San Luis Gonzaga de Ica, ¿no? Y muy contento, muy feliz. Las ponencias todas muy maravillosas, muy bonitas, muy buenas. Muy en
Muchas
especial a la
gracias.
en verdad un reconocimiento muy grande para la doctora, muy
Muchas
locuaz,
gracias.
explícita. Y gracias a ustedes también por permitirme participar como un oyente más.
Muchas
Muchas
gracias.
gracias.
Muchas gracias.
De verdad que nos
Felicitaciones.
alegra mucho que nos acompañes.
Gracias, muchas gracias.
Muchas gracias, Carlos.
Joan
También nos
Alfonso,
escriben
desde la Universidad Conrad Lorenz de Colombia.
y desde Medellín también, Cristian David, desde Nueva Orleans, Néstor Díaz también.
Julián
Tenemos
Hurtado nos
bastante.
dice grande, Maca. ¿Ah? Creo que todos hemos quedado impresionados con su presentación.
Recuerden que si quieren hablar pueden activar sus cámaras y sus micrófonos. Tenemos una pequeña pausa para continuar con nuestro último ponente.
Daniel nos envía saludos desde Bogotá. Cristian, saludos desde Medellín.
Muchas gracias a todos por participar.
Los invitamos a escribir desde qué lugares nos están acompañando. Luis Roberto, saludos desde El Salvador, graduado de la Universidad del Salvador en física, ¿eh?
Interesante.
Muchas gracias, Luis, por conectarte. Miguel, desde la Fundación Universitaria Conrad Lorenz. Lina, desde nuestra alma mater, saludos desde la Universidad del Valle en Cali. ¿Ah? Cómo nos encanta escuchar que estás en la Universidad del Valle ahora.
Claro que sí. Bueno, bueno, entonces, por aquí nos escribe Roberto Martínez, que es estudiante de matemáticas de la Universidad del Salvador, que hemos tenido unas ponencias magníficas. Esperamos poder seguir proporcionando estas conferencias a todos los latinoamericanos jóvenes que estén interesados en estos temas y en muchos otros, ¿no? De las aplicaciones en matemáticas y las ciencias en matemáticas, entre otras.
Miguel Fernández desde Lima, Perú, desde la Pontificia Universidad Católica del Perú. Nos dice que muy interesante la última conferencia. Muchas gracias, Miguel.
Muy bien. Saludos desde Honduras, de Eduardo Cárdenas, estudiante de la Universidad Nacional Autónoma de Honduras. Y también nos dice Daniel, muchas felicidades, muy buen espacio. Muchas gracias.
Listo. Saludos desde Ica, Perú. Soy profesor de la Universidad Salvis Gonzaga, nos dice Carlos. Carlos Aparcaná. Gracias, Miguel. Gracias, Carlos.
Bueno, yo creo que tendremos una pausita adicional de unos 10 minutos más
Y
para
regresaremos.
comienzo con la
Listo.
última charla.
Excelente. Compartir banner y
Mm, everybody. Maybe Dr. Senapati, are you there? We can start your video and your microphone.
Okay, now Professor Senapati has the co-host permission to share the screen.
Please, Dr. Senapati, could you share your screen and open your
Yeah.
camera?
Hi, can you hear me now?
Yeah.
Okay, good. So let me share my screen for a minute.
Okay.
Can you see my screen now?
Yes.
All right.
You can open your camera too, maybe?
A video. Okay, yeah. Can you see me now?
Yes.
Thank you very much. Thanks for the invite, and it's a really pleasure meeting and talking on the quantum computing's industrial applications. Yeah, let me go to my slides. Yeah. So shall we start, or we have to wait for someone more participant?
Mm, 2 minutes to start your presentation, and then you can start your conference. Give me. I think that I can start. Hello,
You can start.
everybody. It is a great pleasure for me to introduce our speaker, Dr. Biswarajan Senapati. He is a consultant with over 20 years of industry experience in topics such as domain consulting, business consulting, and solution architecture for designing large-scale ERP systems. He has doctoral studies in quantum computing, quantum information science, and quantum cryptography from Capital Technology University. And in addition, a PhD in information science from the University of Arkansas at Little Rock. Among his work and developments are the following. He had sub-centers of competence and delivery in the US, Europe, and UK geographies. He has individually designed solutions and been part of the team for multiple opportunities of projects at SAP worth over 100 million. He has experience in quantum computing, quantum machine learning, quantum artificial intelligence, quantum intelligent systems to solve real-world problems according to Industrial 5.0 point, among others. Today, Dr. Viswarajan Senapati will be sharing his thought applied quantum artificial intelligence into industrial application. Dr. Senapati, you have 14 minutes for your presentation. Later, 10 minutes for question. Now you can start.
Thank you. Thank you, and good evening, good afternoon, good morning to everybody. So I'm Dr. Bishwan Senapati. I'm a solution architect, come enterprise architect, and I have been working in industry last 20 years. And this is my key research area. I have been researching a lot in quantum computing. When I say quantum computing, most of us might be knowing quantum computing, AI, machine learning, edge computing, cloud computing. So quantum computing is part of typically it's like a qubits. So in current computing, in classic computing, we use bits, so 0 and 1. 0 for, let's say, null, 1 for, let's, some values. Similarly, quantum computing works on qubits. So I would be talking on how the quantum computers can be useful or very essential in order to maintain the industrial manufacture, or maybe any of the critical or complex problem solving activity, whether it is industry manufacturing or healthcare, automation, or it could be in infrastructure or security applications. We'll talk about more into quantum computers, how it is going to help you, I mean, help all of us, and also how quantum AI or quantum machine learning can be leveraged into our real time, real world problems. So this is regarding agenda. So we'll talk about how the quantum computer is different than classic computers. What are the qubits? What are the quantum operations? And how the quantum algorithm works, how the physical implementation takes place in the industrial side, and any further development research going on. And we'll be exclusively talking about manufacturing, like smart applications, smart industrial application, where quantum computers are heavily deployed, and still the research are going on to build a lot of high volume of qubits quantum computer to be innovates those things. So in this, you're seeing how the quantum computers will change our world, our life, right? So you can see it is operating into different dimension. It is a qubits, and typically, if you look at a quantum computer, is classified as a supercomputing. I would not say supercomputing; it's a very supercomputing, which will operate a formula called qubits, quantum bits, and qubits is nothing but your 0 and 1s. So, but it is a entangle or superposition in such a way the capacity or the capability of quantum computer would be much higher than the standard on the classic computers. That is one of the key criteria. And then the build a quantum computers, you need to have a superficial infrastructure. You have to have a high degree of negative temperature, maybe 300 to 400 degree Fahrenheit temperature you have to have. So it is highly expensive, and to build such networks and such quantum circuits, and then to apply into real time industry, it's really a challenging and demand. So we'll talk about differences. What is difference between, everybody knows like classic computers we have been using, right, since many years. So classic computers talk about 0 and 1s. It doesn't have any kind of inheritance, or it doesn't have any kind of I would say entanglement or superpositions. Whereas in qubits, like quantum computer, we use in qubits. So you can see the bracket 0, and this is a direct notation. So 1, and it has a feature it can be entangle, or it can be superposition to anywhere, any moment at any given point of time. So you can apply into real time, and based on that real time application, you can solve a large or complex problems in the real time scenario. For example, in one of my use case in manufacturing, I've been to manufacturing last many years. So what happened is we generally procure or produce a lot of sensitive equipment, for example, aerospace equipment or defense productions. So it is there are possibility there are some of the industrial espionage maybe happen, or trade secrets that can be that can be definitely mislead to somebody. So we don't want to mislead our production or manufacturing side by wrong hands, or maybe as per the GDPR or CCP application compliances. We don't want to troublesome. So those things will be definitely protected, or privacy security would be definitely there to solve in the quantum applications. So let's see other slides. So typically, if you look at the quantum bits in Bloch-sphere, so typically it is in, you can see the x-axis, y-axis, z-axis, as well as minus x, minus y, minus z. And typically the formula is nothing but the quantum computers are working in the superficial um, like a high capability capacity, where you can use your models, like same data you are using in the classic computer, you can use them, and you can build your quantum AI or quantum machine learning model to solve the complex problem. For example, you are getting a lot of unsupervised data or supervised data, or complex data sets in the financial transaction or manufacturing issues or something, or new product design or development. You can solve those through the quantum computings. So the fact of quantum computings, basically the fact is, like in US we are spending a lot of money, and the DOE, especially in NASA and other agency, they're spending a lot of money to build the quantum computers and quantum mechanics. So quantum computing, again, it's nothing but your quantum physics, quantum chemistry, and quantum mechanics. It has a property for chemical property, it has a mechanical properties, and it has a physical properties like physics. The super, so, all these semiconductor devices, and we build a quantum computer and to make them useful into the real time world. So if you look at the entire overall global market of quantum computers or quantum information science or systems, the place where I'm currently staying, so it's called Chicago, Illinois. So it is one of the world's largest hub for quantum computers. So it's basically government has announced a lot of budgets for the research, for the development, to support industries. Very recent year we had a seminar, a conference. I was driving a quantum computing in international conferences. So we added a lot of quantum use cases to solve those complex problem, let's say in automobile industries, like how the auto-guided vehicle will be track or trace, how the driverless car will be worked through the quantum communications, and how can you manage those. So this is the typical challenges, and we have been doing a lot. And also in the recent year, quantum computing is being used in the to solve the healthcare problems or healthcare issue, the new drug research or new disease research in cancer, all the things. So a lot of companies and a lot of industrialists are spending the money and the time for quantum. So we'll be the entire quantum computers is based on the quantum information processing, like classic computer, classic information processing. So it is a field of study that deals with all the processing of information using quantum mechanical systems, or you can say physical systems. So in quantum information processing, we'll talk about like quantum bits, qubits, how the quantum gates operate, what are the quantum algorithm, whether source or algorithms or any of the quantum algorithm will be applied, and how the quantum cryptography is getting used, and what are the key challenges and limitation for these quantum computings. Okay, and future research and innovations. So as you know, in the classic computers, that's deal with the bits like 0 and 1, fundamental object of yes or no, or some values. If it is a 1, it is called some value it has. If it is no, 0, it has no values, right? So similarly, the qubits, quantum bits, are typically into it has been realizing the using various physical systems such as electrons and ions and photons. Those things will be useful, and when using the electron or a quantum computing system may be used for electron spin. So basically it's been from a positive to negative side, negative to positive sides, and also it has an upward downward spin. So that is the reason between the quantum computers are highly superpositions, and it will highly polarized, so that any of the you can polarize from one angle, let's say up to down or down to up, right? The spin down or spin up. So that gives more strength to solve any of the problems. That's the major advantage of quantum computers. Okay, so here, if you ask, if you can understand like how the quantum qubits or quantum computer are different than classic bits. So of course, yes. So in classic bits, it is 0 and 1. Even quantum bits are 0 and 1, right? But quantum bit has a property to polarized, or to entangle, or to inheritance, or you can use the superposition of the quantum bits. For example, let's say if you talk about two digit bits like 00011011. Similarly, if you talk about the 3 states like 000, 001, 010, or 100, those are 3 bits like 2 to the power of n. So those can be like superposition in such a way the capability of a computing system would be much advanced or advantage. Much faster than the classic computers. And qubit can also be entangled with each other. For example, you have 0 and 1, you can entangle in such a way the entangle of property of the qubits allow their states to be correlated in such a way that the classic computer cannot be beat them. So that is the major advantage of quantum computers. When you build a quantum computers, you have to make in mind that quantum computers are entangled, they have been superposition, they have been like multiple polarized way, so that the capability of the computer would be much faster than classic computers. That's the reason quantum computer highly demands. Okay. Here the quantum computing main properties. What are the major property of quantum computers? So the quantum computer have many properties. So we'll talk about 3 major property. One is superpositions, entanglement, and interference. So so basically in superposition, a qubit is nothing but it's 0 and 1. You can superposition in such a way like you can spin up and spin down, or in such a way then the capability or capacity of the computing power would be much higher. So you can definitely create a complex like superpositions, multidimensional computation space you can create, and this so that the complex problem or on solved problem can be easily solved in these superpositions. Entanglement is one of the property of quantum where it affects the correlate between behavior of two separate things. For example, if you look at like 2 qubits, right, 0110, 00, or 11. Okay, you can change any of the direction to that, and you can entangle 2 of these photons or ions into such a way so the power of the computational power will be much higher. So in interference is typically environment where entangle of qubits are placed into state of superpositions. There are wave of probability, so where the maximum capacity of the computer would be increased, and then you can solve n number of problems or n number of data sets, or on it's not only supervised machine learning you can use any of the machine learning, supervised, semi-supervised, unsupervised machine learning, or any data set you can use in that interference. So we'll talk about what are the quantum interference and what are the use case. In the quantum interference, which is basically this particular like particle interact with the influence themselves, and other particle with the probability superposition state. So you can see those ions or those photons or those electrons will be interference in such a way the probability of superposition will be maximum higher states, and the quantum Fourier transformation will be applied, and the most of the major algorithm like the source algorithm or of the major algorithm can solve those quantum like Fourier transformation, and it can help us to protect the like quantum cryptography. Any kind of secure information should not be handed over to anybody, so that nobody can steal our information whatever we are using into, right? And also it is more stable states and quantum states where we can intervene between the different path, and the quantum Fourier transformation is basically a algorithm which will support you to control or save or secure our protections in terms of like in data transformations, or any kind of you can use like quantum teleportations or whatever things you can use. Some of the use case I have been using in quantum interference is like quantum interference can be used in the quantum computer to perform calculation, especially in the banking and finance transaction you can do. And definitely it used for the quantum teleportations. And the real world example, like for example, if you have a let's say you might be knowing there are two major algorithm, Govers and Peter Sear's algorithms, so that can be definitely applied, and it solve complex problem like business problem. In one of my use case in manufacturing, I've been using both this algorithm, so to solve my new product launch, or let's say we are planning to launch a new aerospace product like engines. So how do you manufacture those engines? Even though we have a common engines we had running since many years, but we wanted to have a fuel efficient, highly sophisticated engine to have a high productivity, right? Those things can be possibly managed through the quantum interference. And the second one is superposition, as we see here in the diagram. So this is the classic bits and versus quantum bits. You can see the superposition is a basically fundamental things where you can position your 0 and 1 in multi directions, and also you can spine up and spine down, and mathematically you can see the bracket is equal to alpha 0 plus beta 1, right? So you can get your superpositions, and it is basically a fundamental attribute of quantum computing. So it can be used in the multi directions or multi dimension, so that you can see those things are fundamentally addressed in quantum superpositions. And in quantum superpositions, so some of the use case I have been using or industry has been using, like one is quantum cryptography. So you can definitely like use the quantum superposition in the quantum cryptography, so that unwanted or industrial espionage can be definitely controlled or managed, and photosynthesis can be definitely possibly managed in the quantum superpositions. And also you can definitely create your own quantum models to support your business. For example, your business has a lot of secret or trade secret informations, you don't want to hand it over to anybody, so you can create your quantum superpositions model in such a way, and you can train the models to make that happen. So that is, and the last one is quantum entanglement. So typically you can see there's a beauty of quantum entanglement is it's a supreme logic, you can say, and it has a lot of connected to, like, say, like consciousness, you can say. It has a lot of things. For example, it's not only science, it has also some kind of spirituality, you can say. So what I mean to say is, so in the quantum entanglement, it is a two different space. For example, let's say you have two subatomic particle, which is intimated by many light years. For example, they have a space, they have been separated from different many light year space, right? So you can get those properties in the quantum entanglement. And basically quantum entanglement is heart of the quantum physics, and still research is going on to make them very successful. And it is being used by quantum teleportations, so quantum internets, it will be coming in future, and quantum sensing and meteorology objects. I mean, the major purpose of the quantum entanglement is quantum communications. Typically, you have seen like quantum key distribution in the ciphertext. We can control, we can manage, we can operate that, and the quantum teleportation could be established in the more secure, safest communication, so nobody can steal our information in terms of industrial espionage or industrial trade secrets, whatever things we can do for encryption. So how the quantum computer works? I mean, how to build a quantum computer? So, I mean, I have a facility to show you the mathematical, how we can operate, or I can create a quantum Q gates and a quantum logic, but I don't have the system ready today. But you can create that. There are a lot of tools that are simulator tool is available in the market. You can use them, and you can definitely go and have research. But quantum computer is built typically a minus temperatures. For example, very cool. I mean, the cooling property would be there definitely because of the decoherence property. So quantum needs a negative temperature of minus 500 or 400 degrees Fahrenheit. So because the electron passes through some different superconductor, and they must have pair. So otherwise, if you don't have that kind of facility, then you can't build a physical quantum computers, and it won't have the same property like quantum superposition, entanglement. Those property cannot be available. So let's talk about this slide. We'll talk about like quantum. How many? What are the type of qubits? Like quantum bits. We talk about quantum bits, right? It's not a classic computer like bits. It's a qubit, quantum bits. So typically there are 7 type of qubits as proposed and implemented in the market. So the first one is superconducting qubits. It's basically the most common type of qubits in the current quantum computing world, and these qubits are based on the basically it is a flow of supercurrent without resistance. For example, superconducting qubits are it's kind of flux qubit, or it kind of a transform qubits or phase qubit. These are the highly used currently, and this is most common qubit in the superconducting qubit in quantum computers. And second qubit is our quantum dot qubits. So these are based on electronic spin states. So basically, it's a semiconductor quantum dots, and this has been used as the material like cadmium or palladium or germanium and indium. So these are the material been used for the quantum dot qubits. And the third one is trapped ion qubits. So typically, it's again based on electronic nature, like the nuclear spin state of the individual ions. And typically, it is used for the material like chemical property called calcium, magnesium, and beryllium. And photon qubit, the third one, is typically these are the based on the such as the polarized phase. So you can polarize and depolarize those things, and this is basically used for the beam splitters and phase shifters. So these are the components are used. And the third one is diamond nitrogen. So this is used, and we call NV, and this is the but typically manipulated using microwaves and optical fields. So these are the used in the diamond nitrogens. And the second last one is topological qubits. This is based on topological property of the material, such as, let's say, some material have a different property like noise or errors. So typically those have been used by topological qubits. And the last one is nuclear magnetic resonance, NMR. So it has been used quite a long time in the various medical field or manufacturing or health, different fields. So typically this is a nuclear spin of atoms or a molecule that can be manipulated using the radio frequency. So you are using NMR, and also this is being used in the quantum computing models. So, what are the key formulas or algorithm in quantum computers? So there are two basic algorithm. One is Gauss algorithm formula. Another one is Peter-Shor's algorithm. So both these two algorithm is highly used, and this has been used in the cryptography or financial transactions or cyber security, manufacturing, a lot of other transactions. We have been using these formulas. If you look at how it is, uh, how it is going to be helpful for our AI or machine learning world. Nowadays, everybody is using AI, Chat GPT, generative AI, or machine learning, or deep learning, or in all of things, right? How quantum computer can be used. So quantum computer is nothing. It's not new, or it's not a different that we cannot use in the AI or machine learning. It is, though it is new, the quantum property would be there, but we can use those machine learning model like a deep learning model or neural networks through the quantum computers like quantum circuits, where we can feed the data, and in the quantum logic gates or quantum Q gates we can see those results successfully. I've been testing a lot. So in the quantum data science or reinforcement learning, you can see quantum information processing is there, and quantum machine learning, that is the core, and the machine learning. So machine learning is the standard classic application we have been using, whereas in quantum machine learning we'll be using in the quantum Q gates, like quantum gates circuit. So based on that, you can use and you can create your own model, you can train the model, and you can reinforce the model to get the better prediction or better results for the data science. So one of my key success or achievement, I would say, I was designing one of the nth order binomial encoder, NOB. So suppose, for example, I wanted to send a information to my colleague who is in let's say New York City, and the information has to secured, protected, and heavily secured, because it is a critical information and it's a government informations. So I was sending let's say I was sending my information through NOBI, nth order binomial encoder. What I'm going to do is, let's say I'm going to send a picture or JPEG or image. So that image I'm converting to binary converters, and then I'm just encoding. I'm just sending decode message, and my colleagues, he will be encode those messages to receive this message. So it's typically, I'm sending from one place to other place, so nobody can steal my information. So if I send just a JPEG image in the email, some hacker can hack my information and then they can steal information, right? So those things can be controlled through quantum qgate, like quantum key distributions. You can see this, somebody is sending the message from computers, it is encrypted, and again it's sending to receiving to by Bob. I mean, it's example he's given here, and he'll decrypt the message and read the message. So now the other third party can read the message. And similarly, if we look at the quantum AI, it's highly used nowadays. So we can use all the AI, artificial intelligence model. Like you can say, you can create your quantum data sets, you can train the model, and you can evaluate the quantum model through the quantum Q gates. These are all Q gates. And then you can definitely get the function, like evaluate your classic model versus quantum model. So you can definitely evaluate and research. So in this slide, I will little talk about, like, how the machine learning. I think most of the machine learning people are used to have machine learning. So the similar way, like supervised machine learning, we have unsupervised, we have reinforcement modeling, or semi-supervised, partially supervised and unsupervised. And the same concept, like all the algorithm, k nearest neighbor or decision tree, random for a support vector machine, whichever, q learning, or all the things would be easily applicable to classic, whereas in quantum we can apply to quantum machine learning, right? We call quantum machine learning here. So like, when I trained a model through knn nearest neighbor, I can say quantum knn. So I can say decision tree, quantum decision tree, or I can say quantum support vector machine, that is for supervised. Similarly, if I wanted to train my model to data set to quantum qubits through unsupervised, I can say q k means, and I can say k neural networks, and similarly reinforcements learning, right? I can use those things in the quantum computings. So it is very easy to use. And some of the machine learning, you can see here how the classic machine learning works here. So typically classic machine learning has the same process. We can train the data, we can select the data, train the model, and make a decision tree. Similarly, quantum model, so we have a quantum processing Q gates. So that model will be give a higher predictions with respect to classic, and also it gives a faster response in terms of, let's say, I have a huge data. I mean, it is very unsupervised data. I cannot control or manage data. It's a real-time data flow from across the system. So I can train the model and I can get my quantum machine learning model through my qubits, quantum computers. Okay. Here, what are the advantage over the classic versus quantum? So if you look at the classic computers, I've been using since many years, and I'm also still using classic computers. But advantage of quantum computer would be the speed. One is accuracy, speed, and it is second thing is privacy and security. As I mentioned earlier, like in a QCAD, we can use that quantum key distribution. All the ciphertext will be distributed safely and securely to the respective party, and then the scalability would be much higher, and it is really a novel application, so you can use and you can predict those things very sophisticated way. Okay. Some of the I would like to highlight in the industrial manufacturing, because I've been working heavily in manufacturing. So as you know, like smart manufacturing is a place where you do a lot of manufacturing contracts you take from your vendor or customers, and you do manufacture those items for the customer or for the vendors. A smart manufacturing is a place where the equipments or robotics or the AI machine learning, maybe Gen AI or quantum AI would be heavily used, or cloud computing, edge computing. It's not manually we can't procure or produce any items or any manufacturing anything, right? We have to heavily depend upon technology, tools, and connected device for, like, for example, IoT, IIoT, or any kind of machines. So if you look at this slide, I was working heavily one of my clients. So all of the smart manufacturing are heavily connected. We call digital manufacturing. So it is connected in such a way each and every equipments or subfloor activity, or you could say machine, human resource, or any of the movable, non-movable items are controlled by machines, right? Or controlled by AI, or controlled by IIoT, or controlled by IoT device or sensor, SCADA, PLC, those things, right? So how a quantum computer can be helping those machines or equipment connected, and to provide a better solution or better like productivity rates, or operational efficiency rates in the manufacturing. So we'll talk about more. So you can see here, typically in supporting tool in the industrial manufacturing or smart manufacturing are, like, you name any of the ERP applications. I've been heavily using ERP applications like SAP, and quantum tools also there, some 4G 5G application or 6G applications, and some of the IoT, MII, like, manufacturing intelligent integration systems, and some of the, like, some of the, you can say, operation and planning software. For example, how much planning you have to make, so that you can definitely control your customer order versus your reseller order. So you have to make your planning in advance, so that you can procure your items, like whatever order you are getting, make to order or make to stock, or be designing any of the new product or new innovations. So you have to make in advance. So for that, we have to have different smart tool we call smart factory. So you may use simulator, you may use like a different manufacturing system, you may use augmented reality, virtual reality, you may use cyber physical system to connect to all the sensor equipments, you may use AI, machine learning, cloud, big data, etc., right? So it is not a one tool. I've been to going to my factory, even though I'm not producing, I'm not a mechanic or engineer, but I know I'm controlling their IT system. So I have to tell them, okay, this is the best practice or best way to manage all of these equipments, right? Connected equipments. So in this, you can see how I was looking into one of the industry 4.0 or industry 5.0. So typically a smart manufacturing or industrial facility needs a lot of equipments, lot of due diligence to connect each and every dots. For example, you have to save energy, you have to have a better production, you have to have a better efficiency on your resource, you have to have a better capability or capacity to make or control the make to order or make to stock. You have to have a quality inspection space, you have to have a dynamic scheduling or virtual scheduling, whatever you have, and smart convergence, so you have digital twins. Those things are literally, we are struggling. For example, if the car market, let's talk about car market. Now the car prices are very high after the post COVID. So why this has been happening? Because we do not know what would be our customer order, right? Or if you know about our customer order, we do not know how much quantity or how much resource we have to procure or produce those car, right? So we do not know that. So that's the main reason we are not able to manage or control the sales and operation planning. How much I have to buy versus how much I have to procure, right? So those things can be easily predicted, or definitely a decision making point through AI or machine learning. But beyond AI and machine learning, we can, if you can train those AI or machine learning model to quantum, this will give a better feature. Very recent time, we had a connect with Volkswagen and Honda. They are also building a lot of quantum simulator to produce those things, so that their factory will have better production rate versus customer. They can fulfill the customer demands in the cars, right? So here is the, like, typically quantum technology being used. So you can see quantum can be used in the different compliances, different product features. You can use that, and also you can maintain the imagining process. I mean, you can use a lot of sensor activity. You can control your IoT, or you can manage everything in the quantum computer. So I was taking one of the data from CIP conferences for manufacturing systems. So you can see how the manufacturing systems like product lifecycle management happen, how the equipment lifecycle or equipment feasibility you can study your human resource versus your technology resources across the plant or factory. Okay. So typically, as you know, we are moving towards 6G, sixth generation communication, real time communication. So quantum is heavily coming with the 6G as well as 5G. So because of ultra reliable low latency, so those are very important for manufacturer. As being a manufacturer, we need to that. And also our most of the factories are maintained through sensor devices and IoT devices. So quantum network is really helpful to make our life much easier, much faster, and also reliable source. It is a secure. For example, if Apple is building a iPhone 16 next year, so this source of all of the product features dimension should not be like steal by somebody, right? It should not be damaged, or maybe the secret data should not be leaked by some hackers. So those things can be easily managed. And not only that, it's like new product. For example, what would be my iPhone 17? How can I save my cost? What are the cost saving model for my iPhone 17? Or maybe let's say BMW X7. So now I'm going to launch a BMW X9 or X10. So what would the cost saving? So every industry needs those kind of tool technology to train the model, predict, and get the expectation beyond the current world. So whatever we can see. This is one of the use case I use, AR VR model, our automated auto guided vehicle, or field maintenance, or plant maintenance model. So some of the my plants highly required maintenance, like preventive versus predictive maintenance. How a quantum computer can be useful to help those. For example, if my plant is 10-year-old plant, I do have a scheduled maintenance, even though um, there are breakdown maintenance. There are some events which I cannot control. I don't have a control over. Even though my factory is overly controlled, managed by IoT, but still I need to do get those devices right. And this is a 6G, quantum 6G. You will be surprised how quantum 6G will come and play a vital role in human lives. So it has a lot of effect, like privacy protections, and it has a lot of technology enabled. So you can have a real virtual world, right? You can see everything in your device. And 6 will be typically it's very intelligent and very deep learning, or you can say you can do anything in 6G. So it is still a way to go. I mean, we all will experience 6G very soon. And then quantum computing with the 6G would be really a highly high demands. And certain application we use in manufacturing practice, our machine, our financial transactions, our data exchange between different system, logistic versus non-logistic system or third party system. And we do a lot of marketing from promotions, even though we are manufacturing something, but we have a competitor, right? So everybody has to in the sync. And then we do a lot of production pipeline, new product launch. Those things are managed by quantum computers or quantum AI or quantum machine learning tools. And yeah, typically it is saving cost, time, and also production efficiency. It is increased production efficiency. Some of the my research, ongoing research I've been doing with quantum QD, quantum key distribution for quantum cryptography. And I'm also doing some of the post quantum safe cryptography, which is still under progress, and quantum cyber security. So that is again one of my area where we can see like cloning attacks or collision attacks or any cyber DDoS or DDoS. So those attacks can be easily manage, or easily can control before an attack happens. Okay. So, and then what are the typical potential benefit? How much benefit we can get from a quantum computers over the manufacturing sites, or maybe real time sites? So we can get huge benefit if we use quantum computer or quantum information science in the better way, or I would say the best practice we applied for GDPR CCPA compliances. We can definitely prevent those on unwanted things or unwanted events which has happened or which will be happen in future. Or maybe let's say COVID, like there are COVID data is available, like before COVID happened, or I mean during COVID happened 2020, so peak COVID time. So you would have definitely used quantum computers. I don't know, whether we have done a lot of AI and machine learning model, right? So similarly, quantum computer could predict, okay, what will happen in my next generation disease, or what will happen in my next gen drugs research. Those things can be easily identifiable. And here are some of the industrial espionage. I'm been practicing heavily cybersecurity, quantum cybersecurity. You can see industrial espionage can happen anywhere, like computer hardware, IT, energy sector, aerospace, automotive, biology, biotechnology, chemical, any of the industry, right? And you can see the cybersecurity biggest area, and there are a lot of investment is happening because of the resources are very expensive, and people are taking a lot of time and challenge. It's very challenging things. And this is one of my research area. I've been innovating a lot of tools in like nth order binomial encoder, NOB we call. So this is a mathematical calculation. So all of the graphic image, I'm converting to binary, and binary to again encode and decode process, and that I'm been testing into quantum computer to get a successful things. Here are some use case, like classic use case. So we have been using quantum. So one is artificial machine learning model we can use. We can use for drug research, protein folding, quantum chemistry, or any of the risk predictions, finance and finance and banking sector. We can do any traffic optimization tool in auto-guided vehicle, weather forecasting, and earthquake. So any of the environmental damage or changes we can manage, or we can see a prediction factor like what will happen in the next 10 years, right? So through quantum computers. And I've been using IEEE I'm a IEEE senior member as well as a student chair advisor. I have been holding a lot of volunteer role in IEEE. So very recent year, IEEE has a lot of standard with respect to quantum. So like quantum software, how it is getting standardized, and post quantum cryptography, any security aspect of quantum computing, any performance aspect of quantum computing, and quantum computing like simulators, how they should perform, or architects. So those are the certain standards. I've been working on that. And here is the 20 year of quantum computer growth. You can see it started with 1998 with IBM and other research centers. So this is really growing. A lot of big companies are really in good space in quantum. And in this quantum industry's perspective, like what are the industry are using, who are the more users. So typically quantum is useful for everywhere, I would say, but the manufacturing, supply chain, high tech, or the infrastructure, security, NASA, or those security agency that are highly using, and Department of Energy is using heavily in the quantum research. So that's all about the today's session. And I would love to have a demo in the real world, so how we can get data and how we can manipulate data into quantum computers. But it needs some time to show the data, but yeah, definitely we could do in near future if possible. Thank you very much. And I would definitely waiting for the questions. If you guys have any question, please definitely reach out to me, or in this forum we can definitely discuss.
Now, are there any questions for Dr. Senapati?
Okay, so I think Carlos has a question. Let me give the permission to Carlos.
Sure.
Okay, Carlos, you can unmute yourself, please.
Hello to everyone. Nice to hear you talking about this, Professor. I'd like to ask you about the topological qubits. Maybe I felt some curiosity about this topic about talking the shape of the things on the level of molecules. Maybe you could help us with some intuition on this, if possible. My second question should be about let's think on the quantum machine learning. What are the main techniques used to encode the classical data you want to train into quantum states? I mean, maybe if you have, let's say, 100 classical data, 100 sets of classical bits. What are the more used maybe methods to transform these classical bits into quantum states?
Yeah, your first, thank you. It's a great question. So I would give an example like a topological quantum field theory. It's really a quantum field theory of topological variants, like invariant variants, both. So it is still under research, and a lot of correlation function or matrix or space time is getting been, uh, being addressed. And definitely it's a really great areas for the quantum topology. And second thing, the second question, like the data with respect to quantum AI or quantum machine learning, you can try to load n number of data, any bits, n number of bits, doesn't matter. And also the program would be same Python you can use, or you can use NumPy, all the things, and you can use the same CNN model or ANN model or support vector machine, whatever supervised or unsupervised machine learning model you are using, you can use. So only thing is you have to create before you use the quantum computers, you have to create a quantum Q gates, that is called quantum gates. Once your system is Q gates, you can program the same way like Pythons. I use Python and pandas, Keras, those things, and programming would be in Python. So you can use those Python and you can pull the data into quantum qubits, and your result will be coming into quantum. It's a simulator. There are a lot of simulator available because the physical quantum computers are highly expensive. So even at the research, we had hardly gets those access. But yes, we have the similar simulators where you can use the data and train your model and test your data and get your results.
Okay, thank you very much for your answer. Thank you.
You're welcome.
For the participants.
I think Tanya has a question.
Sure.
Tanya is asking if there are some applications to law. Tanya.
Yeah, of course. So, so when you talk about law compliances, yes. So there is definitely law and compliances applicable. As you know, the Chat GPT. Let's talk about Chat GPT in classic computer, right? We use Chat GPT, and we say, "Hey, where I can go, where I can get information." But suddenly, the laws has been going to be very strict in any of the Chat GPT or generative AI or AI machine learning. And very recently, in October 30th, US government and UK government has announced all of the Chat GPT AI machine learning should have a standard framework by NIST, and it should not be hamper any of the personal identifiable objects. For example, if I'm my SSN number, I'm using SSN number. So it's not be post or anywhere ChatGPT can say, okay, give me SSN number of somebody. No, I cannot. Some banking transaction file or some social security information or some information related to national security. So those has been controlled. And in terms of quantum, yes, it will be very like in a strict restriction. Quantum computers should not be used for any of the destruction of any things. I mean, any warfare or something like any kind of future, like wars that cannot be used. Those things. It will be definitely useful for the benefit of human lives, or benefit of drug research or cancer or certain great thing we should use. But recently there are a lot of laws, regulation are taking place by GDPR and CCPA and the local body like NIST. So it's still under discussion.
So this what? There are other. Tanya say that thank you.
You're welcome.
Marcial say that thank you. Thanks very much for your nice time. Thank you, Dr. Giswaran.
Thank you very much. I appreciate everyone, and thanks for giving me opportunity to talk about this topic. Thank you.
Very interesting. Yeah. Okay. now or closing. One moment. The one you can share the running. You can. Okay. Thank you so much, participants, the speakers, and everyone for staying. Ladies and gentlemen, as we conclude the ICMAM Latin America Satellite Conference on Data Science, Artificial Intelligence, and Machine Learning, I want to express heartfelt thanks for our speakers, attendants, organizers, and sponsors. Your contribution made this event a success. I invite you to stay connected and join us in future events. Let's continue advancing together in the dynamic fields of science. Thank you so much for staying here. Thank you, really thank you.
So thank you very much. Thank you very much, Alexandra, for this very nice organization. Thank you also to all the participants for supporting our initiative. ICMA in Latin America is an organization dedicated to promoting mathematical research and also allowing to we are committed to allow the young mathematicians to interact with these very nice specialists in all the ideas. So thank you very much. I really invite you to make your registration for ICMAN Latin America 2024 that will be held in October of 2024. So please make your registration. We will have the participation of very nice mathematicians, very nice specialists, Fields medalists, Abel prizes, which somehow is a very good opportunity maybe for young mathematicians. So thank you very much and see you soon.
Thank you.
Thank you, Professor Senabati, of course, for
Thank you.
accepting the invitation of our organization.
Yeah. Have a good night. I think it's a night for you guys, I believe.
Right. Thank you.
Yeah. Have a good night. Thank you very much. Thanks for the invite.
Okay, so we invite all the participants to leave the virtual room now. And we will send you the certificate of attendance soon. So thank you very much.